Wow, started recording already.
That's fast. Earlier than yesterday, I think.
Yep. Thanks for posting that eval link again.
No problem.
Wow, people are showing up later and later every morning.
Yeah, interesting. Where's everyone? Oh, it's Friday. Jason said, recovering from the talk yesterday.
Yeah, I already posted that link. There it is. Yep, it's just scroll up a little bit. You'll see the link for the materials. I'm glad you liked it, Jason. It's pretty cool to watch when you see a VBA that's writing and creating a macro sheet. It's kind of fun to watch and see the results like that. Good grief. I just saw a post on LinkedIn, the Black Hills InfoSec, John Strand. They're doing a 24-hour pre-show banter conathon. Just 24 hours straight of informal conversation about anything and everything to fill the time. That sounds crazy. Wow. little over a minute before we begin. Yes, it is Friday. It is 9 a.m. Great timing, Robert. It is Friday. We have another action-packed day, yet another one, all week long. Welcome to day 5. We're a little short on people this morning for some reason. I'm a little concerned that they didn't get, well, actually the link would just go to Zoom. So hopefully everything is fine and that people are working. They're just slept in this morning or something. So welcome. The 5:30 presentation, I posted the link already. I posted it last night, it looks like. And so it looks like a number of people have already seen that. But it has the link to a folder on my Dropbox account that has the video and it has the sample. And I think I gave the sample, I put the password of, I don't remember. I think I put the password actually in the name of the file. So you should be able to get it pretty easily. Let me see here. Yeah, I put the password as infected. I actually put it in the name of the zip file for the sample. That was because it's probably going to be made available to more people, and I wanted it to be more of the standard thing is that we use for sharing files. So that is up there. I've also posted this morning, it's pinned, the CTF information. So there's a link to a SANS.org website. The username and password is the HTTP basic auth information. That's just to get to the website. And then you need to register an account there and create your own username and password. There's a little register link at the top. Just do that anytime before tomorrow morning. So no rush to do this. But you'll need an account on there to set that, to run that. If you want to use a fictional name, no problem. Use whatever name you want. Just keep it clean. If you want to remain anonymous, that's fine too. If you do win the coin, I will need your real name to know that, so I can send you the coin. A couple more things about the CTF before we get going. The CTF questions have 3 hints associated with them. And you lose 1/3 of the points with each wrong question. So if you miss, with each hint. So if you take 3 hints, you'll lose all the points for that question. However, the 3rd hint will be the answer to the question. So if you get stuck on a particular question, for some reason it just isn't clicking, go ahead and take those hints, because, and then answer the question so you get the points back. So basically you end up with net 0. If you take the 3 hints and then you enter the answer to the question, you'll end up with a net 0 points, but you will be allowed to move forward. And maybe you'll be able to answer the question after that and the question after that. So each sample is independent. So but within each sample, you have to answer the questions in order. But you should not ever have to get stuck on a particular question, because you can still get the answer by using the 3rd hint. It's also a great learning experience, because once you see the answer, you can go back, say, oh, here's why that's the answer. And we'll talk more about that tomorrow. But definitely review section 6 of your workbooks for tomorrow to prepare for the challenge. So yesterday we did a lot of stuff, and the evals. Thank you for the evals. Thank you for the kind comments. There were a couple of comments that said it was a tough day yesterday, and that there was it was sometimes it was hard if you were trying to follow along in your own VM at the same time we were doing it live, and also to take notes at the same time. Yes, that is definitely going to be a difficult thing to do. And especially this afternoon, I recommend not trying to do 3 things at once. Don't try to listen to me and do your VM and take notes, because it's going to be a losing proposition. There's just too much material. It's pretty complex. So what I recommend, especially for the samples this afternoon, is to focus on notes, focus on the presentation, focus on my reasoning behind why I do things the way I do them. So that, and I'm going to show you some pretty cool techniques for speeding up your analysis too, that are not in your books. And those are the things I would focus on today. Then go back through the videos and through the samples, and you'll be able to pause the video and really take a look. Oh, now I see what's going on here, and it will make more sense. You're probably going to need to go through the samples 4, 5 times before they really click. And I'm saying that because that's what I had to do. It's one time through is not going to be enough. These are advanced samples we're going to be discussing, and you'll want to get some more exposure to them and some practice. And same thing goes for the samples we did yesterday. That CoveTour has so many parts to it, you'll probably want to go back over it. This afternoon, we're going to be looking at some more assembly language based items. And so you'll want to be reviewing that too. All is well. Any questions about yesterday's material? Any comments? Okay, well, we're going to do some more fun stuff today. Boy, just look where we've come so far, though. First day was the funnel of fun. Second day, assembly language. Third day, malicious documents. Yesterday, unpacking and code injection and API hooking. Today, self-defending malware. So first thing we're going to look at is, how does malware detect that we're running debugger? This afternoon, we'll be looking at how it will also look for other tools besides. So it might be looking for many other tools. One of the samples that you might have heard of, the SolarWinds exploit. It was written in .NET because SolarWinds itself, that app was written in .NET, and it searched for a lot of different tools. Oddly enough, and it had a pretty complete list of tools, many tools I hadn't heard of before. And so sometimes when you see these, you look at the malware and it shows you a whole list of tools that it's looking for, maybe you want to go look up some of those tools and maybe add them to your toolkit, that they might be pretty interesting. But the one thing that was kind of a glaring miss was it had no reference to Ghidra. It looked for x64 debug, but not Ghidra. I thought that's kind of weird, but whatever. And then it looked for Sysmon, and it wouldn't run if Sysmon was running. Then we're going to be looking at something called process hollowing. This is another one of those buzzwords you might have heard about, and we're going to examine how that works. Then we're going to be looking some more about detecting the whole toolkit, and then malware that tries to lie to us or try to trick us in some way into thinking the code is doing one thing when really it's doing another. And those techniques, because of their complexity, those are the ones I really want you to kind of sit back and really pay attention to the concepts and take notes on those concepts, rather than try to follow along in your own debuggers. And then we'll be looking at some more unpacking, of course, throughout the day. And tomorrow is the CTF. The CTF, people get worried that it's going to be as hard as the samples that we look at this afternoon or as hard as COFTR. They are not. So don't worry about that either. They're going to focus on the common things that you're going to need, the common skills that you need. We will also cover some things in the CTF we do not cover in class. So you're going to need to use your Google Fu to find answers to some of those. There's even some trivia that you're going to have to use your Google Fu to go find. Let's start with get down. So go ahead and start unzipping that. And in this sample, if you were to run it just as is and you were monitoring it with Wireshark, you would see it tries to make a connection to IP address 1.234.27.146. You may remember this from the end of day one. And in this case, we don't have the web server up and running, and so it's not going to succeed. That's fine. We just want to see that it's trying to make a connection to this IP address. But if you run this sample in the debugger, it will terminate right away. So just to get warmed up, let's do this first one together. So one of the things that I do is I'll run it both with and without the debugger to see if it behaves differently. And if it does, it means it's doing some anti-debugging stuff. Load it up in x32 debug, or x64 in this case. I forgot this is a 64-bit program. x64 debug. There we go. So similar to what we did yesterday, we're going to do a little recon. We're not going to go through the steps of running it both with and without the debugger. I think you guys are pretty comfortable with that already. You just fire up Wireshark and watch the traffic. So we're just going to start with at the stage where we've already determined that it runs differently in the debugger than it does without the debugger. Just like we did yesterday, we're going to do a little recon. Search for, in the current region, just look for those intermodular calls. I'm not going to do that because I don't want to give away the answer yet. But when you do that, do you see anything interesting in that list of calls? Yep, very first hit is debugger present. It's the first thing at the top of the screen. So is debugger present right there at the top? And I think there's probably a second one as I recall, but we're going to focus on the first one. So double click on is debugger present to go to the part of the code that calls is debugger present. Highlight the line immediately after that call. Debug, run until selection, or you can press F4. Highlight the line, run until selection. Our IP should be pointing to the address 102A, which is the test instruction. Is debugger present? Now we're going to use our day 2 skills. Now we're going to use our day 2 skills a lot today. Is debugger present returns a 1. What is the register? Quick quiz. What register is used for return values? There's EAX, yep. And in 64-bit code, RAX, yep. So if If you look at the top right, you'll see that RAX is indeed set to 1 because we do have a debugger present. It knows all about it. And so we see the next line is the test. It's testing EAX to see if it's equal to 0. If it's not 0, it's going to jump. And if you hover over that line that has that jump, you get a little pop-up window that gives you a sneak preview of what that code is going to do. It's going to do a little bit of code and return. And because this is at the top of the program, it looks basically it's just going to quit. There's nothing exciting there. So we want to defeat this test. We want to defeat this defense. So if it's jump if not equal, it will jump. If it's 0, then it will come down and do all of its other calls and do a lot of other work. The technique we're going to use is we're going to patch the program. We're going to change the program so that it won't do that jump. In the debugger, we have the ability to change anything we want. We can change the stack entries. We can change anything in memory that belongs to the process. We can change the instructions, and we can change values of the registers. What would you change? And there's no one right answer. I know I've had at least a dozen or more different answers that have all been correct for how you might defeat this defense. So how would you defeat this defense? What changes would you make for this? Change JNE to NE, adding a NOP, yeah, both of those are right. Like I said, there's a lot of ways of doing this. Change RAX to 0, also right. Yep. So let's do some of that. We can change RAX to 0. The way you do that is just double click on that value up in the right-hand corner, RAX. A little window will pop up. You just hit 0. You don't have to have the leading zeros, just put 0, and that will change it. I'm going to cancel so we can look at these other techniques. And says add no ops. And so then, and what would you change to be a no op? After test EAX thingy, yeah, that jumped. Exactly. And then the other one was change JNE to NE. Yeah, I love that one. That to me, that for some reason that kind of hits my funny bone, because if I change a JNE to a JE, it will jump if the debugger is not running. So now this malware will only work if you are running in the debugger. And I find that kind of amusing for some reason. You can change that instruction just by double clicking on the JNE. Oops, that is not the right thing. Let me go back. Hit the star key if you did what I just did. It goes right back. Don't double click. Do right mouse. And they changed the user interface on me. That's what happened. And I used to just do that. It's like, what? Why'd you do that to me? Right. Whatever here. I want to edit it. What have they done to me? If I just, maybe it's just hit the space bar. There we go, hit the space bar. So I highlighted the JNE and I hit the space bar. Now I can just leave all the addressing and everything the same. Just type JE. And you can hit OK. I'm not going to do that because I want to follow Anne's suggestion, and we're going to change it to no ops, because we have to change it permanently so it will work the same way no matter what. You could do that JE and then hit OK, and it will patch it. Let's change that same thing now. Let's just hit spacebar on that JNE. we know that if whether there's a debugger or not, we don't want it to jump. We want it to do its normal behavior. So if you want to get rid of a jump, you can just change it to a no op. Hit that space bar again. Change that whole line to no op and fill with no ops. Out here to the left, you'll see the binary or the hex representation of the code. When we change it to a no-op, it's going to change it to a hex 90, but a no-op is only 1 byte. When you replace an instruction, you have to replace it with the exact same number of bytes or you will break the program. It will crash. So it needs to be the same number of bytes. So by saying we'll change it with a no-op and then fill any differences, this one looks like it probably takes 5, 6 bytes. It's going to give the other 5 bytes, it's going to fill those up with no-ops too. We click OK. And it filled all those 6 bytes with no ops, and we click cancel because we don't want to make any other changes. Now we can actually patch the binary. We have changed this program while it's running, and we can do file, patch, under file patch, and it will show you the patches, and you can select which ones you want. They're already automatically selected all. Click patch file and save it on the desktop. You have to give it a new name. You can't overwrite the file because it is already open in the debugger, so it's locked. Windows has it locked, so you have to give it a different name. Call it get down patched or whatever you want to call it. And then when you run the program afterwards, you will see that it works the same with or without the debugger. You will see the connection in Wireshark to that hard-coded IP address. I'm not going to worry about doing that. I'm going to leave that as an exercise for you guys to do later. So now if I just hit F8, it does the test, but we don't care about the test because it's not going to actually do anything because the jump is now gone and it can execute normally. So there's a variety of things you can do. If you want to get rid of a jump, change the jump to no ops. There are times where you want it to always jump. So instead of a JNE or a JE, instead of a conditional jump, just change it to a JMP to always jump. So with just that simple rule, you'll be able to eliminate the majority of these conditionals. It can get rather tedious to do that because you have to find out where all these conditionals are and you have to turn them off. So if you want to never jump, change it to a no op. If you want it to always jump, change it to a JMP. Very simple rule. What is this actually doing though? What is debugger present doing? I'm going to give you now a look behind the scenes of what isdebugger does. And this is important to understand how it works. In the bottom left in dump 1, click on that anywhere in that dump, doesn't matter. Press Control G. Make sure you click on that dump and then press Control G so we can go to some address. This is not in your books, but it's because I want you to see what's going on behind the scenes. We talked about the process environment block the other day. This allows you to view the process environment block in the dump by typing peb with parentheses, a little function. There we go. So now we see the we can't really make any sense of it, but there's a couple little things I want to show you. Isdebugger present reads that byte at offset 2, offset 0, 1, and 2. So we have offset 2 has that byte of 0, 1, and it returns that byte. That is all that isdebugger present does. So another way you could defeat this defense, you'd have to do it every time you ran the program, but you could double click it and just put a 0 there. I'm not going to do that right now, but you could just put a 0 there. That would work as long as the program runs. Anytime isdebugger present gets called, then that it will return a 0 because you changed it to a 0. The disadvantage, by the way, of changing RAX to 1 is you have to change it every single time isDebugger present is called. There we go. There we go. There's also a byte down here. It's a 70. If you're running a debugger, that value will be 70. That's another function call that is used to determine that the malware might use. So you might need to also change that to a 0. But again, you'd have to do that every single time you run the program. So what if you want to do it? If you don't want to do all this work every time you run the program, go to plugins, Scylla hide. And then there's options. Someone asked the other day if we were going to discuss Scylla hide. Yes, we are. Plugins, Scylla hide options. Scylla hide has all these options and it will do all these checks for you. So hide from the PEB. If you check that, it will check being debugged, heap flags, NT global flag, so on. Being debugged is that byte at offset 2. It changes that 1 to a 0. The NT global flag is that 70 that I just showed you. And then there's some other things in the PEB that it also modifies. We recommend that you only check those items in that left-hand column. Do not check those in the second or the third columns unless you get desperate, because the odds that it's going to crash become much higher. So if you find out that it's not enough to just check that left-hand column, maybe do some experimentation and see if some other ways is checking some of those other options helps. So all those options on the left are the different ways that malware can detect a debugger. You can tell there's a lot of ways it can detect a debugger. So Scylla hide hides the debugger from the malware. That's its whole purpose in life. So let's check those. You can save this as a profile too, so that you can see there's create new profile. You can do that. I just have it disabled for now, but you can play with the profiles later if you would like. So I click on all of those on the left-hand side. I click OK. I get a message saying applied changes, restarting target is not necessary. I don't need to restart the program. Notice that it immediately changed that 1 to a 0, and that 70 changed it to a 0 too. It fixed both of them for us. Now you know what's going on kind of behind the scenes. Also, because you've seen API hooking, Scylla hooks a lot of those functions, those NT functions. So Scylla is hooking all those functions beginning with NT, the output debug string, and so on. It hooks those and returns values hiding the debugger so that the malware can't detect it. An embarrassing experience that I had actually not that long ago. One of the things I like to do sometimes is run the malware in the VM, take a snapshot, and then the snapshot saves the entire memory image in a .vmem file. Then I use volatility to analyze that memory image. And I started looking at that memory image and I said, wow, there's a lot of API hooking and everything going on. What's happening here? And then I realized that when I took the image, I was running the debugger and I had run Scylla hide. And so it looked just like a rootkit. It's like, oh, felt really stupid at that point. Any questions what we've done just now? Yeah, those are the lessons you remember best. Yeah, the ones where you did something, okay, that was not great. It was I felt especially dumb because it took me about an hour to figure it out. I was like, what? So if you're going to take memory images and analyze them, do it without the debugger loaded. Just run it as is, let it run for a while, and then take your memory snapshot. You take your snapshot and you're good to go. let's go back over to the slides, do a recap. So we loaded it up in x64 debug, and after we noticed it ran differently in Wireshark when the debugger was running versus not. We looked in the current region and we looked for those API calls. This one was really nice because and this actually is really kind of typical. If it's going to call isDebugger present, it will usually do it pretty early. So it's not unusual for it to be towards the top. We double clicked on it to go to the CPU window. And we examined the code. We looked at that test and the jump. And we set that breakpoint on the test so that we could see what the return value from isDebugger present was. We looked at RAX register. It was a 1. And then there's some ideas here for what you can change things to. And we've talked about all of these. So the other thing I want to really emphasize is that don't make too many changes. The more changes you make, the higher the likelihood is that you'll break the program. Our Coveter sample, we had an old one that had bugs in it. I tried patching it to fix some of those bugs. And sometimes the patch would fix the bug, but then the Coveter wouldn't run. And it was very confusing. And what it appeared to me was that it was actually checking to see if any changes had been made to its code. So it can actually do an integrity check on itself to see if anything was changed, and then it will fail. So you want to minimize the number of changes so that you minimize the odds that it's going to cause that kind of a problem. So we pick the space bar, right click assemble, that's what it is. Just click the space bar and fill with no ops. And then you could save it if you want. And then we can just allow it to run, and Wireshark will show that connection. Here is the assembly language code that you will sometimes see for isDebugger present. I mentioned that isDebugger present only returns that value that's at that single byte. And remember I said always watch for FS30 because that is returning the address of the PEB. So it's moving the address of the PEB into EAX, and it says go to offset 2 at that location, and then test that for 0. So that's really all isDebugger present is doing. Instead of a test, it's just moving EAX plus 2 into EAX, and that's doing a return. That's all isDebugger present. It's a couple of instructions. Nothing too exciting. There's lots of other APIs, and that's what Scylla Hide is to help us with. That NT global flag, here's some more detail about it. You don't really need to worry about it. When you're running a debugger, there are some extra heap things that happen. The heap is the memory. So there's the other stuff that happens with memory when you're running a debugger that it does some extra checks. This is also one of the reasons why running a debugger sometimes changes the behavior of a program, which drives us programmers nuts, because these things get changed. And so the program works differently when you're using the debugger when it's not. You're just trying to do some debugging. Similar to the being debug flag, there's an NT global flag that is at offset 68 hex, and it just compares that to see if it's a 70. Other things the malware can do, it can check to see if you're doing single stepping. So it will calculate the time A, and then a bunch of code will execute. Then it will calculate time B, subtract time A from time B, and if it takes too long, it's going to assume you're running a debugger and you're single stepping through the code. That's going to be much slower than if it were just running normally. There's a lot of ways of calculating the time, and that second column in Scylla Hide will try to help with that problem. I found that to be hit or miss. Sometimes it works, sometimes it doesn't. It will also, though Scylla is not able to help when it's using RDTSC. That stands for read timestamp counter. So it can calculate the read timestamp counter at the top, do it again at the bottom, and calculate the difference, and if it takes too long. So you might have to look for these read timestamp counters and knock out the checks for the timestamp differences. That gets really tedious if they do a lot of that. And we already showed you it's still a hide. Now we're going to add some more tools to your static analysis toolkit. Exercise 5.2, this is getdown.exe. That IP address, if you do a search for it, if you do strings and look at all the strings, you won't find it anywhere in the strings. So maybe it's obfuscated somewhere. So you're going to see some tools now that will help you deobfuscate strings statically. They don't take very long to run. So add them to your toolbox, run them as a normal matter of standard operating procedure to see if anything's in there. Because if they're trying to hide something, maybe you're using just an XOR 1-byte key or some other mechanism that one of these tools figures out. If they're trying to hide something from you, that means that's probably one of the first things you should look at. And maybe it seems to be very benign at first, but if they're hiding it from you, there must be a reason they are hiding it from you. So this is exercise 5.2. This is get down still. Exit the debugger. And I'll post the poll here in just a second. Pages 16 to 25. So the poll is up. Wow, I see 3 people are not done but continue anyway. That's unusual. Is there anything that I can help you with? Work. Yeah, the usual thing. It's all catching up at the end of the week, I'm sure. Yep. Yep. Work, work, work. Ah, yep. Now on demand is kind of nice too because you get this set of videos that with Lenny on them. So now you'll have a set of videos with me, a set of videos with Lenny. You're going to get 2 perspectives, and that's really kind of nice. Good idea, Arun. Just push them off. Straight arm work. Yeah, you'll want to use all of your books for the CTF on tomorrow. All right, looks like we're ready to walk through this real fast, and then we'll take our first break. So I mentioned this is a set of easy to use tools that you can use to find if there's other information there. XOR search, we're right back with Didier Stevens. Anytime we're talking about text and malware, it seems like he's in the middle of it. And when you did that search, it's a case insensitive. In this case, it doesn't matter because it's numbers. And then the -S says, once you find what I tell you to look for, go looking for anything else that might also be XORed with that same key. And so that it found that XOR 83, and it found there was an affiliate ID, which we talked about before, just part of that whole business model that the crime gangs use. There's some brute forcing techniques here. Looks like this might be scareware, security threat detected on your computer. You got to do something about it. bbCrack tries to score them. If you look at the XOR 20 versus XOR 25, it's not here on your slide. I'm sorry, 5, XOR 05 with 25. You'll see that one is the opposite case from the other one. It just sets that upper lowercase bit. Then you're asked to open this project up in Ghidra, this 9.exe. And this is a pattern you will see not all the time, but it is definitely out there and it is being used. And this particular sample, like I mentioned before, you look for the values, ASCII characters that are between 20, or hex digits, I should say, between 20 and 7F. And all of these match that. Oops, I want just a box. All of these match those criteria. So that's when you're going to start to think that maybe this is what is called a stack string. And it's just creating those strings one character at a time. And because they are not all together, there's these move instructions or in between the bytes of the string. They're a little bit more difficult to detect. And there's this whole process that you can use in Ghidra to change them. You can convert them if you want. I tend to just hover over them a little bit and just see if it's what I think it is, and then I move on. It's a little faster to do it that way instead of having to go through those. Or you can set up a key stroke just to do it quickly. Get a little shortcut. strdOB will let you do it from the command line. And I was thinking, well, how is it doing that? Is it actually looking at the instructions? I actually examined it, and it's just a little short Perl script. It runs a Linux program called objdump to dump the object file. And then it just uses regular expressions to find something between 20 and 7F out to the far right, and then it just dumps all of those and dumps all those characters, and that's what you find. So it's actually pretty effective because of the way it does things. Floss is a little bit different kind of an animal. It's written by FireEye, and it has some heuristics, which means it has some rules of thumb that it uses to find strings, and it does a little bit of emulation. And it will find strings that nothing else will find. It will also miss some strings that the other tools will find. So it's a complementary tool with some of the other tools that you just used. But if it does find things, it might be worth looking at them a little bit deeper, especially in the area that says, we'll see some strings in this next exercise that it finds. So let's go take our break, and we'll come back. We'll look at something that Floss found for us that will allow us to do some more unpacking. See you in 10. Hi, Jan. Back for a test.
Hey, Evan, I can hear you. Sounds good.
Good. Welcome back from break. All right. So where we left off was we had just played with some of the static analysis tools to help us identify if there's anything that they're trying to hide from us that we can find. Obviously, this won't find everything, but if it does find something, it's probably worth looking at earlier rather than later. So we'll start by looking at what Floss found for us with this sample DRTG. So DRTG found this in Linux. We're going to use this information in Windows in the debugger to guide our analysis. On the bottom right-hand corner, you'll see there's some functions beginning with RTL and ZW and NT. All of these are Windows native API functions and are an indication that somebody is trying to make calls directly to the Windows native API instead of going through the official published API. So instead of write process memory, for instance, maybe they're calling ZW write virtual memory, which means if you set a breakpoint on write process memory, it will never, that breakpoint will never get hit because they're bypassing it to go straight to the ZW call. For this exercise, we're really interested in RTL decompress buffer because maybe that is a form of unpacking. Maybe it's unpacking something. We certainly want to see it similar to the crypt decrypt. We want to see what the results of that is. If they're trying to hide the fact that they're calling it from us, maybe we want to see what the results of that function are. And of course, there's others we'd want to see too, but this is certainly the first place that I would look for this particular set. So RTL decompress buffer, again, is in my top 5 or 6. It's right up there in functions that I would look for. So risky API calls, they're suspicious ones. So let's extract that. Let's do this one all together. Extract DRTG in Windows. You can just run it from the desktop is fine. We're going to load up the debugger. This is X32 debug. And once it's loaded, there's a couple things I want you to do that's going to simplify our life a little bit. We're going to use Scylla hide like we just showed in exercise 1. Check all the boxes on the left-hand side. There we go. Save those. Then there's another setting I need you to change. Under options, options preferences is that first option at the top. it's kind of weird. Every time we have a new version of the debugger, we have a new little step we have to add. It seems like there's just a different little quirk to it. This is another quirk that appeared in this latest version of the debugger. Options, preferences, and then the third tab over is exceptions. You'll see it has break on and nothing is checked. Somehow that gets lost in the settings. We don't want to break because this creates a lot of noise, and it breaks and tells us every exception in the system, and the vast majority of them are just noise and they don't have any impact on us at all. So break on and then change that, check the box that says do not break. Click save. And that should be all the settings that we need to do. And what was the name of that function again? That was RTL decompress buffer. So we want to set a breakpoint on that function. So BP decompress buffer. What slide was that on? That was on slide 26 was the name if you need that name. It's also on slide 30, I say here. So if it was successful, it will tell you the breakpoint was set. We're just, now that the breakpoint is set, we're just going to run. I like using the little blue arrow at the top, or you can press F9. Did it not work? Okay, look at my screen, and down at the bottom, it didn't stop on RTL decompress buffer. It stopped at some random location. It said first chance exception. And it's almost like that didn't, and that's the sort of thing you'll see if that exception that I checked, see, it didn't save it. And I don't know why. I had to do it twice. So if you see an exception down at the bottom, it says first chance exception, you're going to need to do the same thing I just did and change this exception thing again and then click save. I can't explain it. It's just a bug in the debugger. Just open it doesn't save it, and you did it 3 times. Wow. Let me see if it works this time. If I hit run again after doing this time. This time I hit run and it did stop at RTL decompress buffer. Yeah, maybe just change it immediately before hitting run, and hopefully you'll get to that RTL decompress buffer. I know that this has been reported back to the developer, but he's making it available for free. So I don't really feel too entitled to complain too much because it's really quite an amazing thing. Yeah, so it probably should have worked now. I can't explain it, but I'll just be patient and let him fix it when he gets around to it. He's done an amazing amount of work for this, and I'm just really impressed that he did this for us. Yeah, there might be a visual bug there, even if it did save it. So now that we're at RTL decompress buffer, this is inside of ntdll.dll. So we need to get back to the user code. We did this once yesterday. We need to get back to user code. So call stack, and that top entry, right mouse or highlight the top entry so it has a gray bar, right mouse click, and we want to follow to. We're going to follow to. So we followed there. We're now at the, now I scrolled up just a little bit so you can see that call to RTL decompress buffer. And that move statement is highlighted. So once it's highlighted, you can press F4 to execute to that line. Press F4, and that's the same as debug until selection. Press F4 to get there. And so EIP will be pointing to that move instruction now. So what I want you to do now, I'm not going to do it because I don't want to give away the punchline. What I want you to do now is press F8 to step over, just press F8 a few times until you see something. Oops, before that, don't press it yet. Don't press F. I made a mistake here. We need to see what was the address that it used to pass into decompressed buffer. Let's look at the documentation first. There's something I forgot. Let's look at RTL decompressed buffer. What we want to find is the uncompressed buffer. We want to find the address of where that is. That uncompressed buffer is going to put some data in that buffer. We want to watch that in the dump. And hopefully I can see that address. It would have been an ECX. We'll see. And let me see if it's the right one. It may not be the right one. Right mouse click ECX. Oops, it's not the right one. Okay, I made a boo-boo. So in that case, I executed too far. So when we do that, I want you to just hit debug restart. We still have the breakpoint set. I told you I was going to do this at least once somewhere. I was going to execute too far, and sure enough, I did. And then we'll hit run to get it again. And it did it again. Options, preferences, exceptions. Do not break, please. And hit run. Now I'm in the right place. That second parameter, remember this little box over here that lists the parameters. That second parameter is right there. We're going to follow that address in the dump window. We want to see what gets put into that decompressed buffer. So the uncompressed buffer is parameter number 2. Right mouse click on that number. It's going to be different for yours versus mine. Follow in dump. Nothing's there yet, but follow that in the dump. So most of the time, if you make a mistake, execute too far, restart, and then run again to your breakpoints is usually pretty quick. It's not too critical. If you do get really deep into an analysis, it's not a bad idea to take a snapshot and then do it again. So that way you can always revert to a snapshot if you get really deep in your analysis and then mess up. So let's do our call stack mechanism again. Call stack again. Right mouse click on the top entry and do follow to. Make sure the move instruction is highlighted. Press F4 to execute to that point. Look down in the bottom left-hand corner. Clearly, it puts something in there. That RTL decompressed buffer, it's no longer a bunch of zeros. RTL decompressed buffer puts something in there. It still looks like it's not readable. But from this point, now that you're at this point, and to get to this point, it is through slides. If you slides 30, 31, and 32. From this point, I want you to just press F8 slowly. Just pause every time. Every time you press F8, watch what's happening in that bottom left-hand window and stop when something changes in that bottom left-hand window. And just pause when you get to that place. And then the Poll is up, just letting me know when you all see something new in that bottom left-hand corner. A couple of people are done. Good. Looks like 3 people are done. I'll just wait for 1 or 2 more people to get done, and then I'll do the same thing myself. So those of you that are done with it, what did you find? Yep, 4D5A, our favorite. Magic Bytes. Yeah, we have any questions about getting to this point, just send me a message. If you're still working on it, go ahead and click on working on it so that I know you're still working on it. Okay, good. That lets me know that you're still there. Okay, good. We're going to continue then. I'm going to press F8 a few times, keeping my eye open on the down below. Hey, it changed. Of course, we want to dump it. Does anybody remember the steps we followed yesterday to dump out that memory that's down in the memory in the dump window? Right mouse click down on the 4D in that window. Follow in memory map. And these steps are on slide 36. Slide 36 is where you right click in the dump area, follow in memory map. And the correct line is already highlighted for you. Don't move that line. Right mouse click and dump memory to file. You know, it's probably an executable. Put it on your desktop. So click on desktop and stage2.exe. This was kind of my standard name. And from that point, we start all over again. Do our static analysis, behavioral analysis, all on that second stage. So it looks like this sample was storing another executable in some kind of compressed format, and it's loading it into memory and decoding it. So it had multiple levels of encoding. It was compressed, and then if you were to look at the code, you'll see it's actually just a single XOR key, XOR byte. But static analysis wouldn't find it because it's compressed and an XOR key. I don't know of any tools that will actually do both of those. It's just too time consuming to do that. And you can verify that it's a valid executable. As usual, drag and drop on PE Studio and see what's there. We're not going to go to that step, but I think we're pretty comfortable with that. Questions? Yet another way to, this would be considered a custom unpacker. It's not really sophisticated, but it's custom. So a lot of your other tools that might get used probably wouldn't find it. So we talked about these custom functions, these native API calls. We don't want to. They get our interest very quickly when we're doing our triage, especially since they're being hidden, and only Floss was able to find them. We set up Scilla hide. Oh, you know what? That's what I didn't do. I didn't click on the line at the top. You have to click that exception filter, which has that address range first, then click do not break. I knew I was forgetting something. And that will help. We're going to do this several times today. So if I forget it again, let me know. I don't know why I keep forgetting that one. Set a breakpoint on RTL decompressed buffer. We run to that point. We follow that second parameter in the dump so we can see what's going to be decompressed to that area. Then we go to the call stack and we follow to that call, and we then run to that location that has that move statement on it, so that we can see what we see down in that dump area. So let's pause at that location. We see some data down there. Take a look at those 7 C's. This is a little bit of a tricky thing that you can see. When you see a lot of 7 C's, especially, this is kind of a pattern you'll see, is that something XORed with 0 is still that something. A XORed with 0 is still A. So if there is a 0 in a particular memory location and it's being XORed with 7C, it's still going to be 7C. And in the header of a PE file, you can expect to find some zeros. And so if you see this kind of a pattern where you see a lot of repeating hex digits, you can probably guess that it's an XOR with the 7C key. Press F8 until you see that data change. We see that MZ. When I teach classes to the Europeans, I have to use MZ. Dump that memory to the file. Same thing we did yesterday. Now we're just going to talk about what is in that dump program. In the dump program, if you look at the imports, you'll see a reference to NT-query information process. NT-query information process is sort of it returns a variety of different kinds of information depending on the parameters passed to it. It's kind of a generic thing. We're not going to open up Ghidra and analyze this one. I think you know how to do that by now. I just want to cover that. But when you go through this on your own, if you want some extra Ghidra experience, just open up Ghidra, load up the dump sample, and search for NT-query information process. At this point, you could look at the code, and what I want to show is some interesting features. If I can find my mouse. So here we have a call to NT-query information process. It needs that first parameter to be a handle to the current process. That's why we see that get current process. Remember, return values are put into EAX. There's another parameter that says, here's the buffer I want you to put the result in. And then it says, this is the kind of information I want returned. That is a 7, which means to return the debugger's port number. When a debugger runs, it actually opens up a network port so that you can do remote debugging. You can have a debugger running on another machine. It could be on your host, controlling a debugger inside of your VM. And you just connect the debugger to that, to the debug code running on the VM. You're controlling it remotely on that port number. So if you are running a debugger, the port number will be non-zero. If you're not running a debugger, it will be 0. So that's what this function is testing. It's going to retrieve the debugger port number. If it's not 0, it will terminate the process. If it is 0, it will do whatever else it wants to do. But eventually it will call exit process if it's being debugged. This is one of the things that Scylla helps protect against. So ordinarily, you don't have to pay too much attention to this. This is just to give you another, a deeper understanding of what's happening with some of these checks that the malware might be making. Scylla does protect against this check. Questions about that technique of dumping a program after using the RTL decompressed buffer. So far we did some static analysis. We learned how to patch a program so that it can be, in this case, how would you patch it? You want it to never jump. If it's not 0, that means the port was non-zero. We don't want it to ever jump. All we'd have to do is nop that out, change it to nops. XOR 1-byte keys are still common. Sometimes they'll use a mix. Sometimes some things will be XORed with 1 byte. Sometimes they'll use something else, some other algorithm, sometimes custom. Use these tools, especially the static analysis, to see if it can guide you to what is interesting very quickly. If you knew about RTL decompressed buffer, how long would it take to dump the next stage? Maybe less than a minute. It's just very, very fast. Once you know what you're looking for, you can speed it up. So next we'll do some unpacking of process hollowing. And then we'll look at some other analysis toolkit detection techniques. This is WinHost 32. So take a couple minutes to unpack that. It's another sample that we'll do together. Let's see, do we need to revert the virtual machines? Probably not this case, because we didn't ever get a chance to actually run DRTG. All it did was unpack it. So you can just close the debugger and you'll be fine. This one is WinHost 32. Extract here. Drag and drop it to the desktop. Oh, maybe I do need to revert. Looks like something might still be running. It's locked anyway. I'm going to revert mine just in case. Sometimes it works if you don't revert. Sometimes it does. So doesn't. So I tend to revert most of the time. We'll need to also look in Linux. So unzip it in Linux too. We'll start in Linux, but I want to get it unzipped in both places first. There we go. So we're going to do some behavioral analysis, actually. Kind of behavioral analysis is, I think, of it kind of a mix of static and behavioral, because we're going to run Kappa. So go to your Linux machines, make sure winhost32.exe is unzipped, and just run kappa. I'll just do it without the -VB first, just to see what happens. See if there's any interesting behavioral categories that we want to look at deeper. So here's the kappa output. It says defense evasion, removal from tools, process injection. That looks interesting. We talked about that yesterday. And specifically, it talks about process hollowing. It found a pattern that matches process hollowing. It also found create process, create a suspended process. Why would a program create a process that is suspended? Why wouldn't it just create a process and just let it run? We'll find out. So a couple of things that are kind of interesting to us. So let's run kappa with the -VV now. And we know that brings out a lot of data. So I'm going to pipe that into less. And then if you do the / search for suspended, you have to use it. The case, it is case sensitive. So you have to do uppercase S suspend, because we wanted to see what function is being called to create that suspended process. And this is really valuable information, this little block right there. It says it's calling create process in kernel 32. And one of the parameters is being passed is a hex 4 that means create suspended. That's how it detected it. This is the rule that was used to detect that it created a suspended process. So maybe we want to go look at that part of the code that creates that suspended process. And we don't know the pattern. We're going to approach this from the point of view, we see something we don't understand. We see something that looks suspicious. It's unusual to create a suspended process. Maybe we can find our own pattern. And so this is the thought process that you would follow maybe when you're trying to find your own pattern. We'll go back over to Windows. Now that we've done our recon, found something that we can target in on. Open winhost32 in x32 debug. Oops, nope, we don't want x32 debug. I want Ghidra. We're looking for a pattern. We could do it in the debugger too. We could do it in the debugger too. We will open it in the debugger a little later. But let's look at Ghidra first, because Ghidra allows us to look around the code just a little bit more conveniently. I think I mentioned the other day, this is part of my standard procedure, is to create a Ghidra project and have it open the debugger at the same time. Let's call it WinHost. You can call it whatever you want. Drag and drop it into the project window. Do the import. Hopefully this is starting to become old hat. Should be able to do this without even thinking about it much. Double click it so I can analyze it and open up the CPU window. Remember to change that checkbox at the bottom. So I put the poll up, so just let me know when you have the Ghidra window open. If you already have the Ghidra window open and it's already done with its analysis, click that you're done, and you can go ahead and move on to searching in the symbol references for create process. And while you're waiting for my machine to get done, go ahead and just kind of poke around that code, look up and down and see what else you see around that create process. Maybe even use the function call trees. Okay. Looks like we have 4 people that are done. Anybody else still working on it that wants me to wait for just another minute? Just click on working on it. Okay. One of the things I found, not everybody is gets on Slack, and so hopefully everybody is on Slack though. So we've got that call to create process. If we see a lot of these are really nice comments that so we don't have to go look up the documentation, but we see a 0.4, 0x4. And that's what Kappa told us. And it said that was equal to a create suspended. So we could right mouse click on that 0x4. You don't need to do this if you don't want to. I'm just showing what you would do. Right mouse click on the 0x4, click on set equate. Type in create. And we see create suspended. We already knew the value because Kappa told it. Yeah, it told us what it was. And there we go. Standard by standard procedure. Let's see what the other calls are. So I always highlight, I click on calls so I can highlight what else is being called. What else do you see being called that might be of interest? If you scroll down, you see some things of interest in this part of the code. Virtual Alec, and specifically Virtual Alec EX with a 40. That makes it really interesting. That was part of our pattern that we saw yesterday with code injection. Executable memory allocated, exactly, Arun. That's exactly what it's doing. And if you want to change that one too, you can right mouse click on 0x40, set that equate. And those names for Virtual Alec begin with page. So page underscore execute read write. You can see that by looking at the documentation. There's a memory constants documentation page. Double click it, and it fills that in. Yep, we've proven that it's page execute read write. What else do you see that might be of interest on that? Flush view of file. Ah, yeah, flush view of file we have not seen yet. Where is it? It's up here a little bit, I think. There it is. Flush view of file, generally you don't need to worry too much because that one, all it does is make sure that whatever is in memory has been saved to the file. So it just syncs up the disk with what's in memory. Write process memory. Yep. So Virtual Alec X, write process memory. Now here we're just saving the address into EBP, but the actual call isn't being made down until down here. There's another call to it down below. And some other things. I'm going to scroll down a little ways. If you go down a little further, you'll see down at 402.2ca, there's a call to resume thread. This is new. Our code injection yesterday, it did a Virtual Alec EX, it did a write process memory, and then it did a create remote thread instead of resume thread. Maybe that resume thread is related to the fact that the process was created in a suspended state. This is a slightly different example. It's doing things a little bit differently than code injection. Let's look at this little green, the function call trees. Let's see if we can see what all is happening. I'm going to full screen that. So we have create process, virtual alloc EX, write process memory, and a resume thread. We're missing a piece still that something is happening with that process. What is happening? So let's look at that. Go click on that create process so we go back to that location in the code browser. We see a call to create process. We also see a call to EDI. What is in EDI? This is another technique you will need to know for tomorrow, but it's also a technique you need to know because you'll see it a lot. So I clicked on EDI so that when I scroll up, I can see where it gets used. There we go. Here we see EDI being used a couple of times. Here's being pushed, so it's being saved on the stack. Not a big deal. Here we get EAX is being saved in EDI. So what is EAX? It's the return value from getProc address. GetProc address returns the value, the address of where a function is located in memory. GetProc address, I'm going to write this out. So address equals getProc address. What does it have to have first? The first parameter, it has to have the handle to a library or a module handle. Libraries are sometimes referred to as modules. So immediately before that, you'll see the call to load library W, and it has the return value of load library is put into EAX. So it's going to be trying to find the address of a function inside of whatever library it's loading. So I'm just going to put H for a handle. We don't need to have anything fancy there. And then here we have the name. I'm going to call it func name is the second parameter. That second parameter had to be pushed somewhere. And what we see is one push for the getProc address. We see another push for the name of ntdll.dll. Load library only takes one parameter. So this push belongs to load library. Then we see another push that has the name, it has a string. That string is nt unmap view of section. NT unmap view of section is just a long name for meaning to delete or free up the memory. That is the executable part. Well, it's actually, in this case, it is the executable part of the program that was just started. So we created a new process. And the code now is going to scoop out its brain. In the decompiler window, nope, that looks right. That looks absolutely right from the decompiler window. Yep. The first parameter is the handle that's returned from load library. If you look in Slack, I'll bring this over. You can see it. Actually, I can't because I'm drawing on the screen. But if you look at that on Slack that Nick just posted, it says the PCVAR equals the NT unmap view of section string, and it gets passed as the second parameter to getProc address. The first parameter is the handle returned from load library. Yep, so it's right. So we know now what it's looking for. It's going to get the address of NT unmap view of section. In other words, it did not want us to know that NT unmap view of section was being called, so it's not putting it into the import address table. It's loading it at runtime instead of putting it into the import address table. That should immediately catch your attention. Now, this is not really the most stealthy way of doing it. if they wanted to be more stealthy, they would also encrypt this name of NTM map view of section and then decode it at runtime so you could not see it in the strings. If you dump out the strings, you would also see this string. So apparently this author just didn't feel that was worth doing it for whatever reason. So the address of that function is put into EDI. Scroll back down to EDI. Now we have the rest of the pattern. We see the call to create process in a suspended state. Call EDI to NT unmapped view of section, scoops out the brain of the program we just started. This sounds kind of gross, right? Anybody ever watched the, what was it? Invasion of the Body Snatchers or something like that? The terrible B movie where you may have heard the term pod people. I think it comes from that movie. So it's the same kind of thing. You're scooping out the brain. When I taught 504, there were a lot of little Easter eggs that John Strand put in there that to old B movies. And unfortunately, I watched more stupid movies that way because I had to see what he was talking about. But now that if we free up some memory, if we scoop out the brain of this victim process, we need to allocate some memory in that process using virtual alloc EX. And then we need to put some new code in that victim process. To do that, we use write process memory. The write process memory gets used to put code to replace the brain. We're doing a brain transplant. This is also known as process hollowing. We're hollowing out the process first and then giving it a new brain. What do we know about the code that new brain is? I keep coming back to this theme over and over again. What do we know about that new brain? Can it be encoded? Can it be encrypted? Or does it have to be runnable? Yep, it has to be runnable, which means we now have some runnable code. We know where it's going to be put into that code. So what if we were to look at let's put a breakpoint in the debugger on address 402.237. Could we not then look at the buffer that's holding that memory and maybe be able to unpack another sample? So let's open this in the debugger. Leave this open in Ghidra, just minimize this because we want to remember that address 402.237. Drag and drop onto X32 debug. My normal pattern of work is to load them up at the same time. So I just popping back and forth between them. When I find something interesting in Ghidra, I'll pop over to the debugger. And when I see something I don't understand in the debugger, I'll pop back over to Ghidra to see if it can help me. So I just posted the breakpoint command with the correct address, BP 402.237. Hopefully I did it right. So set that breakpoint in the command line on the bottom, BP 402.237, and press run. Do we need to do, I might have to do that options. I always forget to do that. The exceptions, click the exceptions, do not break. Make sure you click on that top line underneath the exception filters and then click do not break and then save. And then run. And we set the breakpoint on a memory address. And all we see in the debugger is it's call EBP, which is the same instruction we saw, but Ghidra knew that it was write process memory and displayed it to us. The debugger does too. but you have to look down here to see it in that little heads up display. Because we're going to call write process memory. So which parameter is it that is being used to store the data? We're not going to even let write process memory finish its work. We're just going to look at the buffer it's writing from. We don't care about the buffer that it's writing to because that's newly allocated memory from virtual alloc, but the buffer it's writing from. So we look at is it the base address or is it buffer? It's buffer. It's a pointer to the buffer that contains data to be written in the address space of the specified process. So it's LP buffer, that's parameter 3. Parameter 3. Right mouse click, follow in dump. Huh, we have it again. We just unpacked yet another sample by using write process memory. I told you yesterday that write process memory is one of those functions that is in my top 3, probably. Virtual Protect EX, write process memory, Virtual alloc EX, RTL decompress buffer. All of these are things you want to prioritize when you're doing your analysis. So we have it. All we have to do is the same process we did before. Right mouse click, follow in memory map, right mouse click in the dump window. We've done this a couple times already, so I'm not going to take as much time to explain it. Right mouse click on the line. Save it on the desktop. Call it stage 2 or stage 3. It's stage 2, but in case my stage 2 was locked for some reason, so it was previously. So that's why I did my revert, because I was worried it was still running for some reason. But I reverted, so I don't have to worry about that. Saved it. We have a brand new one. It is time for our break, but I just want to do one last thing. Just drag and drop stage 2 on PE Studio. The usual thing, you start all over again. Anytime you unpack something, you have to start all over. So Nick listed write process memory, virtual protect EX, virtual alloc X, crypt decrypt, RTL decompress buffer. Yep, all of those. Thanks, Nick, for putting that up there. It's all in your notes too, but so you can see we have some strings. They're very readable. We have a lot of imports. It definitely looks unpacked. So we'll come back and do a recap of this exercise after our break. I'll talk to you in 10. Hi, Yen.
Hi, Evan.
You get a good break?
Yeah, I walked through some of the previous materials.
You're supposed to break.
No, so the compressed buffer, I missed that part, so I had to go back.
Ah,
Yeah,
I was reading the notes from SANS, and it said that GoToTraining kind of blew it. They said that we had SANS has an agreement with them that they were not to do any upgrades on us or any of our students uh, without our prior approval. It was supposed to be a manual process, and they messed it up. That's what happened yesterday.
that's crazy because they shouldn't do upgrades, I think, during the work hours or business days.
Yeah, that's the sort of thing I would get fired over.
Right, yeah, it's bad
So
thing.
so they're actually trying to get GoToTraining to switch it back to the quote classic experience. So kind of crazy. I actually personally I prefer Zoom, but I've been using Zoom for a long time. Yeah. Oh, Nick says he doesn't take a break either. Lunch is normally 15 minutes. Wow. I have to get away and stretch and move. That's good for me. So let's recap what we just did. We just learned a new pattern. And this is the sort of thing you would do is uh, find a starting point. Maybe look at it in the function call tree, work through the different calls. Make sure you don't miss any calls because some of them might be disguised by using a call through a register and having used load library and get proc address. So we ran Kappa and we discovered it's creating a suspended process. We thought that sounded weird, and we looked at the detail in Kappa and saw, oh, that parameter being passed to create process was called create suspended. Now we know what API call was used to create that process. We can go right to it. Let's see. Oh, okay, so Nick just posted some stuff about a review of what I did last night. Oh, I'll have to look at that during lunchtime. I'm going to go ahead and pin that if that's all right. Cool. I've been posted on Twitter. Seriously? Wow. I'll have to look. So we loaded it up into Ghidra. I'm not going to go through those steps. We in Kappa. Now we used the symbol references, but Kappa is another thing that will give us some recon information. We could have just gone straight to that address. We didn't even have to open up the symbol references. That interesting code that we're want to look at is at address 402 1AE right there. So we could have gone straight to that. It doesn't matter how you get to it. What matters is that you find it. We saw it was that sure enough, it had to create suspended. We saw that there was a call to EDI that we had to do a little bit more work to figure out what that is. But you'll need it for tomorrow, this technique about get proc address and load library. You'll need it for many samples you analyze too. When we analyzed that, we saw it was calling NT unmap view of section, which is scooping out the process brain. And there's the full pattern right there on slide 52. So we already talked about there's other versions of create process that might begin with NT or ZW, so be aware of that. So you have to look for those kinds of function names too. then but it has, part of the pattern is it has to create a suspended process. And the reason is, what do you think would happen if the process is running and you freed up the memory for that code? It's going to crash, of course. So that's why it had to create it in a suspended state. So now it's sitting there in a comatose state, scoops out the brain, replaces the brain by allocating new memory and writing new code into that memory. Then it calls resume thread because that process was just suspended. So now it just has to resume it, but now it's actually going to be using the new code instead. I see a question coming in. Would having it crash not be a valuable stage for threat actors to fork off of exception handles? You're on the right path. For this particular case, not so much, because the code, it has to already be running. You can only catch exceptions in your own process. Because that remote process that is trying to inject into is not running yet, it can't catch any exceptions. So that isn't going to work. We will see some examples today where the attacker uses exceptions to hide what they're doing and to be very deceptive. So we will do that today. It'll be this afternoon. Those are some of the more deceptive and difficult to analyze samples. So we can just think of this as just another way to unpack. Easy. And the write process memory, this is why it's so valuable, because it's going to be one of two things. You'll either see write process memory used to put a jump or a push return, which means you've got a rootkit on your hands if you see that kind of behavior, or it's going to be used to put some code in that block, which means you've got process hollowing or maybe some code injection. So regardless, write process memory is very useful to look at. And we noted the address 402.237. Now we wanted to see what that code is. We could not see the code in static mode, obviously, so we had to use the debugger. Set the breakpoint there. We did verify that is calling write process memory by looking at that little heads-up display. Then we followed that third parameter, and we knew to follow the third parameter because we went and looked at the documentation. No one that I know of memorizes the Windows API and the parameters. We're using searches all the time. We're using the Microsoft documentations to find which parameters we're interested in. We followed that third parameter in the dump and did our usual steps. We right mouse click, follow a memory map, dump the memory to file, and now we can look at it, do our static analysis, our dynamic analysis, we're all set. On the right-hand side, you can see it uses api.ipfi.org. It's another of those websites that allows you to find the external IP address. If you look really closely too, you'll see there's a .ru reference, subketron or something, .ru. So that's process hollowing is very similar to code injection. The difference is that it's, instead of just attaching itself to the process, it's actually replacing the brains of the process. Yesterday, when we did Coveter, remember there was a Reg server 32 that started up another copy of Reg server 32. So when you're looking at the behavioral analysis, and you might be looking at in Process Hacker, if you see one process that creates another copy of itself, it's probably doing process hollowing, because it doesn't have to be its own process. Reg server 32 could have started up another copy of some other program and injected into it. But what if that program isn't there? What if it's not on the system? Then it's going to fail. The program that it knows is always there is a copy of itself. And so that's why you see it running as a copy of itself. And WinHost 32 does the same thing. You will sometimes see programs that will start up a copy of service host, and then they will process hollow that service host and inject into it. That blends in really well into the system. What if the Stuxnet? You're probably familiar with Stuxnet. It also did coding process hollowing, but it created a second copy of LSASS, which there's only ever supposed to be one copy of LSASS running at a time on the system. So that one was a little bit more obvious. There we go. So nice reference. And yep, Copter does process hollowing, exactly. And you saw that yesterday, but you didn't know the pattern until just now. So go ahead and pin that if you would, Anne. That's a good reference to keep around. So, and we saw that the address, the call to that NT unmapped view of section was actually trying to be stealthy. So next, we're going to see a couple of examples of malware that uses different mechanisms to either detect the analysis toolkit or to keep the toolkit or to keep the malware from running if a toolkit if it's running in a sandbox, for instance. Maybe it won't run in the sandbox. There are so many techniques. We're only going to be able to touch on some of them, but you'll probably be able to use your imagination and be able to say, oh, yeah, this VM is a little bit different in some ways from a real system. What are some of those ways that it's different? In fact, go ahead and post on Slack. What are some of the ways that you think specifically that malware might look for in a VM that wouldn't be present anywhere else? One CPU, yeah, look at the number of cores. What else? There's all kinds of things. Just think of what's different. You have CPU. There's some generic stuff here on this slide, but maybe you could be a little more specific on it. Detected peripherals, yeah. What kind of peripherals, Jason? What do you think might be different? VMware tools, yep. USB items, keyboards, mice, yep, because they all have some identifiers. And they might be specific to VMware or VirtualBox or anything others. No activity, yeah, that's another big one. Automated interaction with the sample. What about disk space? Do your VMs tend to be the same size? They tend to be pretty small. Maybe it's less than 500 gig nowadays. That might be an indication it's a VM. Sometimes VMware tools, what about registry keys? Maybe some registry keys are different. One of the interesting ones for VMware is it actually creates a new CPU instruction that only exists inside VMware. And so if the malware tries to execute that instruction and it succeeds, it knows it's in a VM. Another one, inability to call out. Yes, if it can't reach out to the internet, and I think, is it WinHost 32? I think if you did some more analysis of WinHost 32, I think it's this sample. Not 100% sure. It might try to reach out to Google. And it actually checks to see if the returned page to see if it's got the Google information on it. Running iNetSim, Fiddler, Network Miner, Wireshark, any of our tools. Yep, all that stuff. Excellent. So you kind of get the idea, and it's a huge list. It's basically, I found it to be impossible to create an environment where it can't detect one or more tools or can't detect that it's running in a sandbox. At least not when I want to monitor what it's doing. MAC addresses for network NIC cards, specific ones for VMware. video controllers. You see some of those on here. Files, processes, registry keys, all that stuff. Some of these sandboxes will actually copy the sample to the same name all the time. And so if it does that, all the malware has to do, am I running as file name XYZ? And then it knows it's done. So you want to keep things as close as possible to the environment that you found the malware in. But there's only so much you can do. Mouse cursor moving. How long has the machine been running? If it's only been running for a few minutes, what do you do in a sandbox? You run start up the sandbox, run the sample. Sandbox has only been running for a minute or two. That would seem a little suspicious probably to the malware author. So we have to figure out ways of patching the code. We can do that using the same techniques we did this morning, or we can change the analysis system. I found that to be difficult. I found generally I'm going to have to patch the code. So we're going to answer some questions now in bbprop. bbprop is using a function called set Windows hook. This is a different function from API hooking. This is a Windows API call that's used quite often. I used to use it when I worked for a company called ETS, Educational Testing Service. If any of you have taken the GRE or the SAT, those kind of tests, MCAT, LSAT, they all come from ETS. And I wrote the original GRE test prep, and I wrote it in Windows 2. That's even before Windows 3. You had to run it from the command line. And we used set Windows hook because this was back when people really were uncomfortable with GUIs. They didn't really even understand scroll bars. One of the weirdest things that I saw, it was just called window back then. Yeah. One of the weirdest things that I've ever seen was that because people were uncomfortable with scroll bars, I wrote some code that used set Windows hook and also did some other things to monitor the keyboard and mouse usage on the system. And I would monitor the scroll bar to see when it was at the bottom versus when it was at the top. And I was told by management, you have to put the words top you have to put some indication at the top so they knew they're at the top, or when they're at the bottom of the text if they're scrolling through some text, because people might not know how to use that scroll bar. And that's true. That was a big problem back then, believe it or not. And so I put the word top when it was at the top, and I put the word bottom at the bottom. It went to the internal, we called it the Political Correctness Committee. And they said, no, you cannot use the words top and bottom. That is too racy. And you need to use the words beginning and end. Who knew? I never knew that was actually a thing. So you see weird things, but there are valid uses for set Windows hook, especially for computer-based testing or some monitoring on usability testing and things. Set Windows hook is used quite a bit for this for computer-based training as well. So we want to answer some questions. Which type of event does this sample try to hook? Which function will be executed when the desired event type occurs on the system? So what kind of event, what functions can be done, and how does this help the malware protect itself? We'll do this one all together. This is one of those that you might want to kind of kick back and watch and take notes on. And since I'm just going to use Ghidra, let's cancel that. Get the code browser, close that. I'm not actually going to close it all the way down. I'm just going to create a new project. Follow along if you want, or just kind of hang out and take notes. Because on this one, it's a little more important to just get a firm understanding what's going on. Oops, I did it wrong. Oops. And drop it. There we go. This one won't take very long to load. It's a lot smaller sample. What we're going to look at is how does it use this set Windows hook. We also learn a new technique on sometimes Ghidra and IDA and other tools can't recognize functions. I like the samples that have misleading icons. Yep. So set Windows. That's the only one in here. We only have one call, so we're going to go straight to it. I guess I should close the there we go. Let's go to set Windows hook. Okay, we're there. This is another one of those. There it goes. It just took it a second. Looks like I still might be doing some analysis. I thought it was done. So here it did our analysis. We see the comments out here. It says the ID hook. The ID hook for set Windows hook is the kind of event that it's going to capture. Rather, I know you can go look at the documentation, so I'm going to just tell you all Windows hooks, the types of them begin with WH underscore. So right mouse click, set the equate. Again, just feel free to just kind of hang back and watch this one. We've done all these steps before. Type WH underscore, and you get three options. Which one do you choose? Well, programmers need to know if the event is within a certain range, and so sometimes you'll see a min or a max. Most those you can pretty much ignore. The programmer is using them as other ways, not as parameters. Instead, the parameter will be the actual type, which in this case is Windows hook mouse low level. That's what that stands for. You would see that in the documentation. So it's actually hooking mouse events. It's going to monitor for any mouse events. And I fixed that one up. The next thing we find is the second parameter is hook proc, or the hook procedure. And it has a long pointer to the function. So the function that it's going to call is 4010B0. And if you want to, you could right mouse click that and give it a label and just say that is mouse hook. And that's what I didn't actually give that. I need to do it in another place. Luckily, Control Z is the label, put it at that address. I need to go to that location to make the label. Control Z at least is a undo. I can double click that address. Oh, that's why it didn't find it. Here's something funny. Would you consider that subtract to be part of the prologue or not? Is it part of the prologue? What do you think? Yes or no? Or don't know? Yeah. Nope. Yeah. I see a no. 50-50 shot. Yeah, exactly. Yeah, 50-50 odds on this one. But take a look. What is it supposed to do? When you subtract from ESP, going back to day 2, that means it's allocating space on the stack, which means it would be part of the prologue. But it doesn't look like a prologue we've seen before. But it's doing one of those two tasks. It's allocating space or it's saving a register, in this case, allocating space. The next line, it is saving a register. And we're used to seeing push EBP being first. So we know there is a function here. We know that because that is what the set Windows hook is passing. It's what's being passed to set Windows hook. This will be called every time a mouse event happens. Ghidra doesn't see it. It doesn't recognize it as function. There's nothing here with parameters or anything else like that. So we have to tell Ghidra there is a function here. This, I don't remember if this is in your books or not. IDA has problems the same way. I don't know if with this sample for sure, but I know that every tool has problems if it doesn't see what it thinks is a standard Prolog. Just a little bit different, it gets messed up. So we can right mouse click on that subtract. We can click on create function. Watch what happens. How cool is that? Now we have a function. We know how many parameters are being passed. We know how many local variables there are. All of that is awesome. And we can change this label, edit that label to say mouse hook. I couldn't do that before. Cool. So sometimes you have to, and so I said on day 2, I said we look at the prologues and epilogues usually so we can ignore that code, but sometimes because we need to tell the disassembler where the functions exist. We have to give it a kick in the butt, basically. So we found parameter 1 and parameter 2. I'm going to make this a little bit wider. There we go. A mouse hook, this parameter 2 is the W param. That's a word size parameter. If you look at the documentation, that is where it tells this mouse hook what kind of a mouse event it is. This mouse hook is handling all kinds of mouse events. They can be mouse moves, mouse button down, mouse button up, mouse clicks. Which mouse button is it? Is it left, right, middle? All of these things are being passed in here. So parameter 2 is what tells it what kind of an event it is. And that became easy to know from telling the Ghidra that there was a function there. So I'm going to highlight parameter 2. I want to see how it's used. Parameter 2 is moved into ESI. So now that I see this moved into ESI, now I need to track ESI. ESI is being compared with 200 here. What is 200? All Windows events begin with WM. That stands for Windows message. So that's going to begin that 200 since it's comparing that W param with 200. Right mouse click, let's see what one it is. We can do that set equate thing that we've been doing. Notice how it becomes very useful here. We can actually tell Ghidra to look these things up for us if we know that it begins with the WM, of course. So I type WM underscore, and it's only found 2 hits, mouse first and mouse move. Similar to that max logic that I mentioned earlier, mouse first is going to be used by the programmer. There'd be a first and a last. But mouse move, we need something more specific than first and last. It's going to be mouse move. So it's going to compare and see if it's a mouse move. If it's not a mouse move, it will jump to this address. So let's do that logic first. I want to see what happens if it's not a mouse move. We'll come back to this code and see what happens if it is a mouse move in a minute. So let's just double click on that entry there. If it's not a mouse move, it's another compare of ESI with a 201. Again, we know that ESI is going to be that W param. Set equate. We don't know which one it is. WM underscore, it's a button down this time. Okay, so now if it wasn't a mouse move, and again, if it wasn't a mouse button this time, I go to another address. Now it compares it with 202. Same process, set the equate. This time it's pretty easy. There's not very many matches, so I just see WM L button up. Mouse button, left mouse button up. So somebody has pressed the mouse button and then released it. So that's when the mouse button is released. You can think of this as a nested if. If it equals, if it's not equal, mouse move. Then if it's not equal, what's the other one? Mouse button down. Else if it's mouse button up. See a question coming in. I can just imagine us entering cheat sheets into old school gaming code console to get this exe to run. Yeah. Yeah. So here we go. What happens if it's not a mouse button up, it jumps up, and we'll see what that code is in just a minute. I want to see what happens if it's not a mouse button down. It's not, what was the first one? Mouse move. So if it's not a mouse move or a button down, what is it going to do? But let's see what happens if it is a mouse button up. It will call another function called unhook Windows hook. This implies that it doesn't care about the Windows hook anymore. It's going to stop monitoring for mouse events. And in fact, that is exactly what happens if you look at these other two calls. I think it's specifically that second one, that's where the malware code eventually starts really running. Up until that time, it is monitoring until it actually sees a mouse button up. This code has always struck me as a little weird. Why does it doesn't need to check for a mouse move or a button down? Because if it's a button up, of course it's not either one of those. So this is unnecessarily complex code, probably just to make it a pain to look through more than anything else. Or it is also possible it's just a dumb programmer. I don't know which one. So is this tagging an educated guess based upon experience? So the tagging with the WM underscore, it's not actually based on experience even. It's just me being lazy and not showing you that set Windows hook and not using the documentation. If we go to the documentation, we can see that ID hook, they all begin with WH. So that's how I knew to look for WH underscore. And somewhere down here, there's going to be a mouse. There it is, mouse LL. That's the one we found. And for that, we then had to see what that hook procedure is expecting. We had to go to low-level mouse proc. And so this is the function, the mouse hook function that we've been looking at. And we look at code, the first parameter, it says how to process the message. If code is less than 0, then the hook procedure just calls get next hook. And it calls get next hook because there might be more than one program that is interested in mouse messages. And so when I'm done with it, I have to be a good citizen and pass it on to the next in line by calling get next hook. What about get wparam? Wparam, when I look at the documentation, we can see what it expects. They all begin with WM underscore. So the tagging is all done by looking at the documentation and then going back. I was just being a little bit lazy. Lparam tells it all about what happened with that. So the wparam says what kind of mouse message it is. Lparam says what is the position of the mouse? Was it which mouse button? It's all, there's a bunch of other stuff that can go on with that mouse. Just a bunch of data we don't care about. Because in this case, the code only cares about what kind of mouse event it was. Did that answer the question, Robert? So when you do this in real life, you are going to have to spend more time playing with the documentation. And notice we haven't looked at any assembly language that we didn't see on day 2. Those 14 base opcodes, they're pretty useful. In fact, I don't know that we'll even get to any of them that aren't on that list. I just don't use them very much. So what happens in the other case? Let's pick the other case now. I'm going to use the back button, go back up to where we were. There's the button up. I want to go to the button down. There it is. So here's our button down. If it is a button down, it does some other work. And I talked about the code blocks a little bit. Now we're really going to start using code blocks, because code blocks are where the program makes a decision. And I look for the end of the code block before I analyze the middle of the code block. So if it's, let's see, this one, the end of the code block here is the jump. It's going to be a jump of some kind. Then if it is a button down, we'll execute these lines of code. I'm not going to analyze them yet because I want to see what happens eventually. And it's going to jump to 4010F1. I click on that. Then I look for the next end of the code block. And it calls a function. Well, it just returns, but it returns after passing the event to the next hook, if there is one. If there isn't one, it just gives it back to Windows. So we see it's not doing anything. It just basically calling the next hook and going back. Let's go back and see if it does the same thing for the button down. Here it is. Here's button down. If it is button down, it's going to just fall through. We want to find the end of the code block. Sure enough, it falls through. All of them do the same thing. They all end up at this same call next hook. So except this case, it jumps up to OF1. So there you go. So we found the address. We found the kind of message, the kind of events being handled, mouse events. How does this help protect this sample if it's running in a sandbox, for instance? What do you think? How does this protect the sample? Yep, maybe you've got a sandbox that isn't mimicking the mouse and moving it around. Exactly. So the sandbox will never trigger the malicious code. If you're doing this by hand, it's probably not going to be a problem because you're going to be clicking on things and eventually it's going to see a mouse up. We just follow the same things we always do. Same steps. So WXE. So when you see these codes, your first thought should be go to the documentation. I did not know the specific type of event, but I did notice that Windows Hook from my Windows experience or from the documentation, they all begin with WH underscore. So I just looked that up and Ghidra helped me find it. Yeah, I guess the step I showed of defining a function, of creating a function, isn't in the book yet. I think it is going to be added. I made that suggestion, but I guess it isn't here. But it is really useful because now you're telling Ghidra, do some more analysis for me and tell me what the parameters are. And then you get the names. You get the param1, which is wparam, and you know where it gets moved. It's getting moved into ESI. And that becomes very handy. You know that from the documentation again for that low-level mouse proc. And it starts comparing it with mouse move. And if it is a mouse move, then it's going to fall through and call next hook. If it's a button down, it's eventually going to call next hook as well. If it's a button up, it will unhook. And that's sort of our first clue. If it's going to stop being interested in mouse events, that's going to be the place where it's doing something that we don't want it to. So it will slow you down a little bit because you have to find out where the real malicious code is. It's not going to be straight through. You're going to have to set a breakpoint on that mouse proc and see what it's interested in and see how it handles each of those events. It's probably faster to do that in the debugger and do it dynamically and just see how it handles. It's a little funky with the debugger because when you're clicking around, is it clicking in the debugger or is it clicking in the program you're trying to debug? I always hated debugging code that uses mouse events because of that reason. We're going to stop here. You get an extra 10 minutes for lunch. We are right on time. Very happy for that. Just a little bit early for lunch, which is, I hope you don't mind that either. I will see you back here at 1. I will be launching Slack as usual. If you have any questions about anything we've done so far today or anything during the week, go ahead and post those. And I will see you at 1 o'clock. Hi, Ann. We've got a little over 10 minutes left, so I figure I'll do an early check today.
Hi, Evan. I can still hear you.
Always. Good, good, good. Let's see. I wanted to go take a look and see what Nick posted. I didn't get a chance to see it. There it is. Maldoc is spreading Dridex malware. Ah, there we go. Who posted that, I wonder? Looks like the same sample that I used. Oh yeah, same URLs and everything. Ah, so question Chad has, do you have daily go-to news sites, tech related? Twitter is probably as good as just about anything. I use Twitter a lot. Dark reading can sometimes be okay. I'm not on the right machine. I have some RSS feeds, but I don't look at them nearly as much as I do Twitter. Okay. Top 3 to follow. Have, actually, my top news site is Google. I just search. If there's something I'm interested in, I search. In terms of following along, Reddit. I definitely follow Reddit. There's some malware Reddits that are good, subreddits. Oh, top 3 Twitter users. Ah, oh, boy. I just look at what's on my list of what's showing up today, so I don't know that I rate them. Hasharazad is really good. I really like Hasharazad stuff. She's got some great tools. And so, actually, if you just look on my Twitter, I'm eDigert. My Twitter handle is eDigert, so I'm easy to find. And just take a look at who I follow. I don't follow just anybody. It's almost all security people. So I would say if you take a look at those and see which ones are interesting to you, I would follow those. I'm just looking at Twitter right now. I see some good stuff, a lot of it about malware. Ah, yeah. So Arun posted a Didier Stevens workshop on YouTube, and I really like his videos. They go through things very methodical, very logically. I actually did pay for his PDF workshop, analysis workshop, 3 or 4 years ago, and because he does so much for the community, I decided I'd good idea for me to support him. They weren't very expensive. It's like $40 for the set. But uh, so I definitely do periodically look at his blog too, because he does some good blog stuff. You keep track of his tools because he's always adding new things. If you find something that one of his tools doesn't handle, you can report it to him. He'll probably add it. Yeah, you can tell just about everything on my Twitter feed there is security. About 5 minutes before we start up again. less than a minute. Oh, I got to see who is registered now. Russian Panda, somebody put some hex in there. I guess now I have to convert it someday. Let's see, F, A, something. Russian Panda, NPAR, ER21. Cool. I had a student one time that he had, his name was I'm definitely not Lenny Zeltzer, or I'm definitely not Lenny. You already converted. Nick, yep. Yep, Professor Falcon, it is 1 o'clock. Welcome back, everyone. Lunchtime is over. And before I start, and just for Nick, I will tell you I had some curry chicken that my wife made, homemade, her own recipe, awesome stuff. It is yummy, very good stuff. And she makes it just the right spiciness. I like spicy food. So this morning we covered some unpacking using process hollowing. We looked at some other unpacking using RTL decompressed buffer. We did some debugger detection and how you would patch a program to get past those defenses. We talked about a way of, if you want it to jump all the time, you change it to a JMP from whatever conditional jump it is. And you just tell the debugger, just change it. It does it. And then if you want it to never jump, you change it, whatever jump instruction it is, to no ops. Nice, simple rule. And minimize the number of changes because you don't want to break the sample. And the more changes you make, the higher the probability is that you'll do that. Then we looked at VBProp. We saw that one of the things that a malware might do to avoid being analyzed inside of a sandbox, it just means sandboxes need to do even more all the time to try to keep from being detected. And sandboxes, they might even have to do things like a lot of hooking of the Windows API calls so that they can hide from the malware, just like Scylla Hide. It's sort of the sandbox equivalent of Scylla Hide. So this next one is a rather long sample. This afternoon, we're going to do some more of this toolkit detection. That's this first sample. Then we're going to be talking about malware that really tries to deceive us and make it really a lot more difficult to analyze. And then we'll look at another way that a malware sample to wrap up the day that tries to hide some behavior, and in doing so leads us straight to what it's doing. I love it when malware tries to hide something, because as soon as you see it, you go, haha, that's what I want to look at first. It's like when you have a kid and you ask them, what are you doing? And they say, nothing. You know, they're doing something. Let's take a look at ROS. This is another one of those that I think you'll want to kick back, take notes on, because even more than the, and this one is the debugger, even more than the, I'm going to revert my virtual machine. Even more than what the malware is doing, I want you to focus on the technique that I'm going to show you for analyzing the sample, because it will apply to many samples. RAAS.zip. And it's X32 debug. All right, let's go and dig into this one. This is an interesting one, and there is a punchline at the end. A lot of samples, maybe you haven't seen a lot of things in this sample. If we looked at the strings in this thing, in fact, let's take a look at some of those strings, because I think that this isn't part of the exercise. I just want you to see that this may not have all the strings in it that you might think it does. It's not so much that it's packed, but it does something else. There are some strings for sure, but the strings it doesn't want you to know about, it hides. So it does show you that it's doing a lot of things, registry, a lot of kind of standard stuff, but create tool hub 32 snapshot is kind of suspicious. It looks like it's going to iterate over some processes. Those are all in the strings. Some crypto. Don't see crypt decrypt there, but it looks like it does do some hashing. We're going to see there's some other strings that are not in here though. There are lots and lots of strings, but there's some of these that we're going to see are not here. It's still enough in these strings to make me suspicious that it's makes it worth looking at. What is this sample doing? First of all, I start looking at it, and this time we're not going to start with we don't have something to start with on this one. We're going to pretend we don't have a starting point. So we're just going to look through the first few instructions and see if there's anything going on. We see some calls, and the calls are, when you see a call that does not test for the return value, I tend to ignore those. It means it's probably some kind of utility function. And that's, I just know that just from my programming background. I've written many utility functions. They don't have a return value. Their whole purpose is just to do something. And so I just let it go. Maybe it's going to do something in the with the parameters, but if there's no test, I don't really care. Then we do have a end of a code block here with jump if not equal after the call to get module handle. That is just a test to see if there was an error. Basically, I think that we'll take a look at it here, see what it's checking for. Maybe that's an error, maybe not. If it's an error, it looks like it jumps to 4013BE. And if I hover over that, you see a little pop-up window that immediately exits the process. Well, get module handle returns a handle to a DLL. So if it finds a DLL in memory, the EAX, the return value, will be non-zero. So it says jump if not zero to this code. So it apparently found a DLL loaded that it didn't like. And we see 4013BE is the exit area of the code. Let's F8 just a little bit. Either follow along if you can. Again, this has a lot of moving parts to it. I recommend taking notes. I recommend watching and then coming back to this exercise later and walking through this yourself. But I want you to especially take notes of the things that I mentioned for the techniques. So I pressed F8, F8 again, F8. We press F8 again until I get to that get module handle. Can we see what it's calling? Can we see what the parameter is here for EB20? EBP minus 20 looks like it's checking for a DLL called dwmappy.dll. We'll come back to that because that's kind of weird. What is dwmappy? If you search for it, you'll have a tough time finding out exactly what it is because it's kind of it's a Windows DLL and it's not very well documented. So if it finds a dwmappy being loaded and it's not going to, EAX is 0, so we know we don't need to worry about that. So maybe that's some kind of a defense. The other thing I like about this little heads up window is this information down here. says that jump is not going to be taken. So if that way, if I'm watching that window, I don't have to try to figure out, well, what is EAX? Is it going to jump or not? The heads up window tells me. Get process heap. Looks like it's getting some memory, allocating some memory. It's just another memory function. Then it's going to call another function at 402BD6 is the address of the function it's calling. Immediately after the function, it tests EAX. And if EAX is not equal to 0, same as the jump above with the get module handle, it jumps to exit process. So quite possibly it's looking for code and it's looking for things in 402BD6 that it doesn't like. And if it doesn't like something it finds, it's going to terminate. The first technique I want to show you is to highlight that line after each of the calls. One of the problems that happens, you start diving into these rabbit holes and you don't know how to get back out of them. So set breakpoints at various places so you can get back out of those rabbit holes. So I set a breakpoint immediately after the call so that if I get too deep in 402BD6, I can get back out really easily. So to dive into this call, EIP is already here. Press F7 and that will take you into that call. F7 is step into, F8 is step over. So I need to step into that. Step into, and we'll start seeing some code. Hold on just a second here. I need to mute my phone. There we go. Should do it. You probably can't hear my phone ring when it goes off thanks to this, but that's good. Let's take a look. So we see a lot of calls. None of them have a test after them until we get down here. So what I will normally do is come straight down to this call. I will click on a call that has a test right after it, load library in this case. I'll press F4 after I highlight the run to selection. And it looks like it's going to load user32.dll. No problem there. These other calls, not too worried about those. I'll talk about them, but we won't actually examine them. So load library, it's going to succeed. It just checks to see if it's an error. If it fails, that means it couldn't load 402C18. And why doesn't it do my little pop-up? Don't know. Again, in my little drop-down, it's in my little pop-up, or not pop-up, heads-up display, it says jump won't be taken. Not a big deal. Then it's going to call get proc address for block input. It didn't want us to know that get block input was being called. And I'm pretty sure the block input does not show up in that list of strings. So it was probably deobfuscated or decoded somewhere either in 40334A or 4033302. Those probably have some kind of a side effect that deobfuscates that string. What does block input do? And this is a fun one. If you, let's get over the get proc address. And it's not taken. So EAX is the address of get block input. And we know that because that's the return value from get proc address is EAX. So we see a call EAX with one parameter of 1. So I'm going to let that 1 be pushed on top of the stack. Block input will make it appear that your machine is hanging. And you have to use Control-Alt-Delete and then just cancel to come back, and that will break out of block input. But if you do happen to step over that call, your machine will appear to be hung. Quite often I get students that get a little bit eager and they just keep hitting F8 a lot. Their machine gets hung and they reboot their virtual machine. So they just reset the virtual machine, revert back to a snapshot. I'm not going to be that mean today. But that parameter is already on the stack. I can change what's on the stack too. I can double click on that one, change that to a 0. And still a hide is supposed to protect us from it. It doesn't always. I think it is protecting us nowadays. I think they actually fixed it with the latest version. But just in case, I'm going to change that to a 0 so I don't have to worry about it. What's next? So that's the first check. That's the first anti-debugging thing that it does. And then I keep going down. We also see now 403.34a. I'm just going to 34a. 34a keeps getting called repeatedly over and over. Scroll down some more. And again. And again. You can see it gets called a lot. This is a common pattern you'll see for a deobfuscation routine. If they have a lot of strings that are obfuscated or encoded, you can detect that just by seeing how many times a function is called. So do we care how it's doing the deobfuscation? Not really. According to the results-oriented malware analysis technique, we're looking, let it do its deobfuscation. We'll just take advantage of it afterward. But we've identified where it's happening. We could go into it, do some reverse engineering if we cared to. So what I'm interested in now is finding these ends of the code blocks. Let's just highlight each one of these JNEs and just press F4 to see what it's doing. Actually, I want to do the calls. Let's do the calls before the JNEs. Because then I can look at the parameters that are being passed to the call. We know it's going to call get module handle W, but I want to know what module is it looking for. So I pressed F4 to run to this selection. What is it looking for? You see the parameter off to the right-hand side? What is it that it's looking for? You can see the name of the DLL, but what do you think that DLL is? AV, yeah. So it's looking for AVG hook X, right? Let's just press F8 a few times to see what else it might be looking for. AVG hook A. So we got some more. We don't have any of these loaded, obviously. What about this one? The 34A is doing some more decoding. It's moving the address of find window into EDI. So we'll see a call EDI. This is that same technique we saw with moving the address of the function of move process, the write process memory and NT unmap view of section. And it will call find window. Now it's calling find window to see if there's any window that has a class name of Ollie debug. So it's looking to see if Ollie debug is loaded. Let's see what else it might be looking for. I'm just going to press F8. Don't worry if you press F8 a couple too many times. This one isn't going to be a problem. Now it's looking for win debug frame class. Let's see what else it's looking for. There's a bunch of these, right? Just keep going down. Now it's looking for immunity debugger. Kind of get the idea. So I'm going to go down a little bit further to where we see the code look a little bit different. Notice we see a pattern of code. We see the deobfuscation followed by a call. Deobfuscation followed by a call to the thing it's looking for. So let's get past where it's doing all of that. If it finds any of those entries, it finds any of those debuggers, anything it doesn't like, it does a jump to 402 EFE. Stay, don't move mouse, there we go. And it will XOR EAX to set EAX to 0. It will increment EAX to set EAX to 1. So EAX will be 1 as the return code if it finds one of these things it doesn't like. So presumably the caller of this function, the back out at the top level, will be checking EAX to see if it equals 0 or not. So I'm just going to scroll down a little longer because I don't want to go through every one of those. So here we have the check, we have the obfuscation and the call. Oh, now we have something different though. Now we have some kind of an 7FFE02D4. Whenever you see a 7F, that's probably a Windows system address in Windows 32. In this case, it's a hard-coded address, which by itself is weird to see that kind of an address be hard-coded. Something must be there. So I'm highlighting that line. If you want to get caught up, if you got lost at any point during this, press Control G, and you can type in the 402D03 address. I just typed the address in case you need it in the chat. If you're not trying to follow along, you're just enjoying the show, great, take a lot of notes because this next part's important. So I highlighted this area. I'm going to press F4 to run to this D03 address. We made it past all those find windows. We have the summary of everything it looks for on the slides. None of those things are things that we're running, so it didn't find anything. 7FFE02D4 reads 1 byte from that location, puts that into CL, then it checks to see if CL has one of the lowest 2 byte sets, a 1 or a 2. It's testing to see if it equals to 3 because that address will have a 3 stored in it if a kernel debugger is loaded. We are not using a kernel debugger, we're using a user mode debugger. So that will not have a 3 in it. If I press F8 just to see what happens, you can look over at ECX. ECX equals on my machine B80F with some zeros. CL is only the lowest byte, so it ignores everything else. So this will not jump. It will not find a kernel debugger. Now we see a lot of other calls. And every time it comes back from one of these calls, it tests to see if EAX is 0 or not. If it's not 0, it jumps to the code that sets EAX to 1 and returns. So clearly it found something it didn't like in any of these other functions. So we're going to go deeper into the rabbit hole into some of these. We're not going to do every one of them because it's just too crazy. This first one, the 6C2, is a bunch of checks for the debugger. And because I forgot, of course, to set Scilla hide, this is what always reminds me to set Scilla hide, is that I know that function has from previously looking at it. But if you want to save yourself some time, you should set Scilla hide before you ever run the sample. It's a great time saver. There we go. Let's save it. And we do not need to restart because it automatically right now it went through and did all of its hooking. Then let's go to options, do those preferences again, do those exceptions. Do not click, make sure to click on the filter on the left and do not break and then save. Now it's saved. Because Scilla hide is protecting us from everything that's happening in 6C2, we're not going to dive into that one. And so I'm going to press F8 to just skip over it. And if you look on the right, we see that EAX is indeed still 0. So it did protect us against everything in 6C2. It did not find anything it didn't like. We're only going to look at the next 3 of these calls. So I'm going to set some breakpoints. So if I keep going down the rabbit hole into these calls, I can get back up to this middle level. And then from this middle level, I can go back up to the top level where I set that first breakpoint. So a good use of breakpoints is a good use of breakpoints to get back to where you were. And maybe you get down the rabbit hole and say, oh, I know what this does. I want to get out of here. You can just hit F9 to run and it will stop at the breakpoint after the call. So let's do some of these. I just clicked the little gray blob out to the left. And we're only going to do 3 of these. So let's just click. I just want to be able to get out of them when I'm done with them. So if you're following along, I recommend you do the same thing, because then if you get lost, you can just hit F9, watch the screen until I get to the next one, and you'll be caught up. First one we want to look at is that 4019AC. So I go to that line and hit F7 to step into. So press F7 to step into the 9AC. we see a lot of calls to that 34A again. So it's doing lots and lots of deobfuscation. And there are no code block ends. There's no ending to code block. So I just scroll past until I start finding the end of a code block. Here we have some code that looks different, but I still want to see the end of that code block. Here's one. Let's just stop right there. I'll set a breakpoint there, because I know it has to execute all of the instructions between where the EIP is now and where I set the breakpoint. It has to execute all of those, because there are no other jumps. And this technique is the same technique I used even the first time I analyzed this sample, because I recognized there's these big code blocks. Let's let them do their thing. Even before I recognized there was a 34A was a deobfuscation routine. Then I pressed, after I have the breakpoint set, I pressed F9. And when we press F9, what is it looking for now? It's looking for 1, 2, 3, 4, 5, 6, 7, 8 different DLL names. It deobfuscated those and put those into those memory locations, and the debugger gives us a little peek at what's in those memory locations. That means I didn't have to analyze each statement all at once. All I had to do was find the end of the code block, let it do its work. It's really efficient, very fast. It's a technique I want you to add to your toolkits for sure. Let's scroll down a little bit. Not too far. There we go. There. So looking carefully over to this left-hand side, I think if it finds one of these, if it finds a DLL, get module handle will be not 0. So it will jump if it's not 0. So it will jump to this 401A58. So it'll jump to 41058. A58 sets EX to 0, adds 1 to it, and it returns. So if it finds something it doesn't like, if it doesn't like one of these DLLs, it will set EAX to 1, and then it will return. And as we saw in the call to this function, then it will also check EAX, set EAX to 1, and return to the top. So we're 3 levels down now. Well, let's assume that the first one it doesn't find. I'm going to hit F8 now. This is always hard when you're trying to see something on the screen. Look where EIP is. It's on the line that has the gray. It's going to increment ESI. And let me go one more. Then it's going to compare it with 8. And it's going to jump if it's below 8. And it's going to jump up. If you look over to the left, you'll see the red arrow pointing up. So we have a loop. So let's do a little review of loops from day 2. This is just a refresher. You start at the bottom of the loop to figure out where it is. The body of the loop is where that red line goes. The red line starts at A54 and points up to A42. That is the body of the loop. What is the control variable? It is ESI, because it's comparing ESI with 8, and that's a stopping condition. It's when ESI is not below 8. It's updating the control variable every time through the loop by 1, adding 1 to it. That's increment. What is ESI equal to? To find out, we have to scroll up just a little bit, and we see ESI is being set to 0. So it starts out at 0, gets incremented each time through the loop until it equals 8, and then it drops out of the loop. It's no coincidence that there are 8 different DLLs that it's checking. So it's going to check each one of these DLLs one at a time to see if they are loaded in memory, and there are various different security tools. Some of these I don't know. It looks like something related to debugger, API log, directory watch, whatever they might be. So what happens when it doesn't jump? What if happens when ESI is equal to 8? It will fall through the jump and the JB, it will fall through that JB and do a jump to A5B. See that little arrow pointing down is A5B. What that does is it skips the XOR and the INC. Because get module handle always returns 0 if it didn't find a DLL, we know that if it gets to this point, where it gets to this jump here, we know if it gets there, that EAX will be 0. So by skipping over the XOR and the INC, we know it is going to return the return value in EAX of 0. We're not going to execute through that whole loop. None of these are on our systems. So right at this point, I know that I'm safe. I'm not running any of these things, any of these tools. I press F9 to get out of this particular little rabbit hole to go up to the mid-level. Oh, I got a breakpoint. I need to turn off my breakpoint. Yeah, if you put the breakpoint in the loop, of course, it's still going to execute. Stop at the breakpoint every time through the loop. So hit F9, we're back out of that 9AC rabbit hole that we dove into. So if you're got lost at all in there, you can still get caught up easily by typing Control G and type D2C. I'm going to let me type this in here and then I'll answer the question. Oops, I meant to write D2C. You can do a go to this address and then you can press F4 to run to this address. So that's, I'm going to do that same thing. Pressing F4 to go to that address. So the question is, can you determine at this point what it does if it finds these DLLs or AV? Not yet. All we know is that it's setting the return address, the return value to 1 and returning. That's all we know at this point. We will be able to tell what it does after we finish all these checks, but we can't tell yet. So next, we're at this point. If you do a Control G402 D2C and F4 to get to that address, and then F7 to dive down into this next little rabbit hole. Here's A61, which we just dove into. Looks very familiar. Lots of calls to the deobfuscation routine. So just scroll down until we reach the end of those, because we already know from, this is a pattern that you've seen already in the code. So you take advantage of that pattern. Just keep scrolling down. There's a lot more going on here, a lot more. Scroll down a long ways until you see the code start to change again. Now we see a lot of these moves and the load effective address. We saw that in the last one. We saw our XOR ESI in the previous one. Scroll down past all of those. We still haven't even found the end of a code block yet. That's what we're looking for, end of a code block. Add this to your toolkit. The speed is so much better if you do it this way. So this time, let's see, we're in the same place. We have the same kind of a thing, but now we don't have a call to get module handle. We have a call to some subroutine at 401724 right here, and I'm going to just hover over it so you can see what is happening. So that little pop-up window, what do you think this function might be doing? I'm going to highlight that and press F4 to get there, and then it will become much more clear. F4, go to that point, and then hover over that. So what do you think that function is going to do? So quick quiz. What is this? What do you think from what you see on the screen? Can you tell what it might do? Have any thoughts? Yeah, it does take a snapshot of what is currently running. Remember the snapshot, the Create Tool Help 32 snapshot, we saw it yesterday when we saw some code injection. It was looping over all of the processes. And for each one of those processes, then it could inject that process with whatever code it wanted to inject with. So why might this code need to loop over all of the processes? We can see the process 32 first. So it looks like it's probably setting up to loop over what's running right now and see what to do with it. Well, what are this? Look at the names of some of these. Wireshark, Community Debugger, Procmon, Process Explorer, IDA, DumpCap, FileMon, Autoruns, Process Hacker. Good, I'm not running Process Hacker right now. That's a good thing. Ollie Debug, TCP View, all of our many different tools. And because it's Windows, and this is still kind of weird to me, but Windows, you can't just say, is JoBox server running right now? You have to loop over all of the processes that are running and compare the executable name with the name of the process you're looking at in the loop. So for every one of these executables that it's looking for, it has to loop through all the processes in memory that are running right now. If any of them are running, then it will return a 1. And we can see that on the next line. It's testing to see if EAX is 1. We already see this pattern. It keeps testing for EAX for 1 for anything it doesn't like. But it can't call get module handle for executables only for DLLs. It has to do more work to detect if an executable is in memory. And what does it do? This loop is identical, except this time our loop is down here at where does the jump of below. This time if jump below if ESI is less than hex 19. Hex 19 would be 16 plus 9 would be 25. So there are 25 executables it's looking for as compared to 8 DLLs. And we have a very small loop there. So it's going to check each executable one at a time, call the 724 function to see if it's loaded in memory. And then if it finds one it doesn't like, here's one it doesn't like, it jumps to C9F. And C9F is right here. And so it sets that EX to 1 and returns. If it doesn't find one it hates, then it jumps down to the POP and EAX will still be 0. So it will return 0 if it doesn't find anything it doesn't like. So once again, because I have my breakpoint set on the caller of this function, I press F9 to get out of this lower function. I don't want to execute this loop 25 times. I already know what it does. So press F9 to do that. So the next interesting address that we want to go to, 402D39. So if you were had missed any of that, you can type Control-G and go to the address I just posted, if you're following along. And then you can go to that address and press F4, and you'll be all caught up. I like setting this up using milestones. And this is exactly the technique that I use for any new sample that I see a big code block. I'll just jump down to the bottom of the code block, and a function might have 4 or 5 or more code blocks, but I want to get a bigger picture view before I dig down into the details of what's happening inside the code block. Because lots of times I don't care too much about what's the inside. I only care about what the result is. What decision is it trying to make at the end of the code block? So we're going to, this is the last one we're going to dive into on this sample. This is D4C. And I'm hovering over it just to see if it's doing the same thing that we saw in the previous two. And I see a reg open key, so it's doing something different. So I definitely want to dive into it. And I can do the same thing for all these other functions. If I hover over the 37C, it looks like it's looking for some more registry keys. We're not going to go into those, but you can kind of see that there might be a variety of techniques that it's using. I actually do recommend looking into those as homework if you're interested to see what else it might be checking for. And you can get a sneak preview just by hovering over them. But we're going to F7 into D4C. You can also restart this sample and immediately just go to this address and then run to this address and you'll be caught up again. It can only take you a second to do that. F7. This time we're not sure what's happening. Let's take a look. I'm going to hit F8 because I'm not quite sure what's going on yet. Oh, we have a very tiny loop now. I always watch everything. I watch out to the left to see if there's a loop that's that we're going to be entering. This one decrements EAX and then it moves 0 into that memory location that's pointed to by ESP plus EAX plus 138. And it looks like EAX is going to be 800 hex. That's a long loop. I do not want to go through that. So it's just initializing a buffer 800 hex bytes large. And now I want to show you how to get past that loop. I highlight the line after the loop and I press F4 to run to selection. Now all those, now that buffer, wherever that is, has been initialized and I didn't have to wait for it. So let's find our, here's moving the address of reg open key into EBX, but we still don't have a, there we go. Now here's the call to that reg open key. So we're looking for the end of a code block. And here we found one. It's going to call reg open key. And if it found something at that key, if it's able to open that key, I'm not sure what it's doing yet. It looks like it'll probably probably do the same thing that it's been doing. Let me, come on, pop up. You were doing just fine earlier. It's not going to pop up for me. I'll jump down here first. So let's jump down to this F4 that's on that line calling EBX. And to see what it's trying to look at, I can click on the next line. You see there's this in the heads up window. When I click on the next line, I can see what it's trying to open. What do you think it might be trying to find in the registry key? What might be stored at that registry key? Any guesses? You don't have to be right. It's just, I'm just hoping you get a guess. What even uses SCSI now, right? Exactly. Great comment. So it's looking for hardware. Maybe, yeah, it could be a SCSI, any kind of SCSI device, hard drive, tape drive, it could be anything. Let's hit F8. Let's see if we can see what it's looking for. We have to hit 8 a few times. And don't try to do this yourselves. I just want you to see what it's looking for, just for informational purposes. Later, when you have more time, I recommend that you might hit F8 yourself and go through it slower. Let's just hit F8 until it looks like it might terminate, and maybe we'll see some other information. As I hit F8, though, I'm watching the right-hand side of that CPU window. I want to see what strings are being decoded to see if there's a string that it might be looking for that it read from the registry. Oh, there it is off the right-hand side. Looks like it finished decoding something. It's looking for a VMware hard drive. So Dan, you asked about SCSI, VMware. You can still set up SCSI drives in VMware. And so that's what it's actually looking for. It's looking to see if you're running VMware. It's looking for an older version of VMware, which I find really not too bright on the part of the developer, because Why didn't they just do a search for VMware instead of searching for this very specific string? Then it would have caught all versions, but that's not what they did. So it's actually, this function is looking for to see if you're running VMware. At this point, I can hit F9. That's all I want you to see in this one, is just there's a registry key that is related to some kind of hardware that's on the machine. Hit F9 so I can get out of this function. And I'm back up here now. I'm back up to where we call D4C. These other functions do similar things. They're looking for other tools. They're looking for other registry keys, registry entries. So definitely take a look at those. And I think there's even more if you scroll down further. Yeah, there's more down here. As you can tell, there's a ton of those. There's a very deeply nested loop that I find bizarre. Looks like it's going to create a process. Not, a bunch of stuff it might be doing there. We don't care about all that. We just want to see the defenses the tools it's looking for. So I'm back up here where I ended up. I'm done looking at this middle function now. Now I've decided I've got a pretty good idea of what's happening. And if anytime it doesn't like something, it jumps to that EFE and sets EAX to 1. I've got a pretty good idea what's happening. Let's hit F9 to go right back up to the very top. I'm done with this rabbit hole. I say I got a good idea. It is an educated guess, but it is a pretty good one, I think. Hit F9. We're back up to the top. Remember, we looked for that get module handle, which had that DW mappy. And then we called BD6, and we set that a breakpoint on the test after it. Did BD6 find anything it disliked? And how do you know? What did every one of these functions have in common that it did when it didn't like something? EAX is set to 1, so it found something. Yep. So how would you now defeat this defense? What would you patch in this part of the code? So if it finds, if it found that EAX is 1, and it's going to exit immediately. So what would you patch? AND's not patch. Okay, we're going to call it AND's not patch from now on. Yes, indeed. Yep. Click on that. ANP, there we go. I highlight it. I highlight that jump if not equal, change it to a NOP, fill it with NOPs, hit OK, and then cancel because we don't want to change anything else. You're famous, Anne. So from now on, if you save this, export, if you patch the file and save it, it will run successfully without any, at least from BD6. Everything that it did in BD6 is now absolutely worthless. And as I first saw this sample, I was wondering, what is that talking about? Why would they make it so easy to knock out one instruction? And it made me think, well, maybe it was two different programmers. Maybe there was one programmer that wrote a library, a detection library, and he is selling it to other guys that are out there, other malware writers. And they maybe not be such good programmers. And of course, it's going to be marketed as that, hey, if you use my library, you'll be able to detect all these tools, and it's really comprehensive. And of course, they'll take it at face value. They say, just call one function. So easy, call one function and check to see if it returned a non-zero. If it returned a non-zero, just stop. So it leads me to believe there might be two different programmers here, two different abilities. I am going to patch this one because there's something else weird that I want to show you. Let's patch that file. And I discovered this by accident. I'm going to save it on the desktop. This is ROS patch.exe. Sounds good. It applied the patches. Awesome. I'm going to get out of this one. I'm going to close this one. This is not in your books, by the way, because I discovered this by accident. So we have ROS patched. We're going to put it into X32 debug. Kick back and watch this because this is crazy. And so this is ROS patched. Let's hit F8 a few times until we get to that get module handle. That very first get module handle. It's looking for DW mappy. If I press F8 one more time, it returns a handle, a valid handle in EAX. So DW mappy, for some reason, is now loaded. What did we do that would cause DW mappy to be loaded? I made this a challenge to the Munich class, and nobody figured this out. And I didn't figure it out until late another night. Actually, on Friday night, I figured it out. And purely by accident. I was actually researching something entirely different. It turns out that DW mappy is part of the UAC functionality in Windows, user account control. And it gets loaded if UAC, it needs to be applied to a program. Well, what did we do that could possibly cause it UAC to be all of a sudden necessary? Well, all we did was change one instruction in a file. Well, look at the icons. There's the original ROS. There's our new ROS patched. And it now has a shield on it. If it has a little shield on it, it means UAC will be loaded. Run as admin. Now, that's actually a good guess. I had so many guesses on this, and none of us got it right. It is because I named this file ROS patched. If I call it, if I get rid of the patched part and call it ROS2, watch what happens. The shield goes away. If I put patch back on or type in or name it with setup or any other thing that might be related to setup or install, the shield comes back. And I accidentally found it when I was researching some UAC stuff in the middle of one of the Windows UAC posts on their website. It says this is their installer detection technology. If you search for installer detection technology, you will find that UAC is automatically applied if the file name matches certain patterns, or if it looks inside the program and sees anything that looks like it might be related to installers. We'll see RegShot has a little shield, regedit has a little shield because it looks like it does stuff with the registry, and so it puts UAC on it. You can change those names, but it's not just names. Microsoft does not document all of the ways that they do that. But what this is telling me in terms of ROS is that ROS says, if UAC is being applied to the program, I'm not going to run. So you can fix the problem just by changing the file name. It kind of blew my mind when I saw that I could just change a file name and change how UAC is applied. All right, let's do a recap and then we'll take our first afternoon break. Set up Scilla Hide. We did our initial recon. We saw that it was initially looking for that DW mappy. And then we saw that it wasn't loaded, so that wasn't a problem. Then we looked at the 402BD6. We saw if 402BD6 returns non-zero, it's just going to terminate. So that means we needed to look at 402BD6 right away. And there's a lot, there is summary of everything in your slides. There's even a really nice summary of all the checkpoints and all the milestones at a slide towards the end of the exercise. So we stepped through the early part of BD6. We saw that it tried to call, well, it did call block input. Down the bottom left, you'll see it says EAX with block input, which if you actually executed that without Silahide, or if Silahide isn't working, excuse me. Then block input will make it look like your machine froze. You can change the top of the stack, and that's fine for this. I think Silahide may work now. Hold on just a second, I need to take a note. There we go. Silahide actually does work now, but it didn't used to. So that's why we say if Silahide couldn't handle it, then you can modify the parameter on top of the stack. And as we did F8, we saw AVG hook X. Ollie debug, we saw that it was using both get module handle to look for some DLLs, and it was using Ollie find window to find the different debuggers. I used the different addresses just so you could help get back in sync if you were following along. But when you're doing the analysis, you don't really need to pay too much attention to the addresses if you set your breakpoints right at the nice convenient stop points. And so on 78, it shows you the different debuggers it's looking for. It's using find window W to find those different debuggers. And then we saw something different. We saw that hard-coded address that will have a 3 in it if a kernel mode debugger is running. And so that would be like WinDebug. And we skipped over the 6C2 because that's just debuggers checks. And those are all protected. We're hidden from those checks by Silahide. So we jumped right into the 9AC. And then we used our knowledge and understanding of code blocks to go to the end of the code block and let it finish doing all of its decoding. So we could see the names of those DLLs. We saw the little loop, really perfect example of a loop for you to practice on. And we saw that it's checking for 8 different DLLs. If it finds any of them, it returns 1. Continuing these steps in class is optional. I did go ahead and continue those steps. Then we hit F9 to go back out. The other option is to do what it says on 81 here. You could execute till return and then do another step, another F8 to get out of it to go back up 1 level. I prefer to using the breakpoint F9 because I can set as many breakpoints as I want. And I just find it's fewer steps, fewer keystrokes. Whichever you prefer is great. I think Nick was saying that he's lazy too. I'm lazy, no question. So we went into this next function. We saw that it had 25 different executables it's looking for. And to check for each one of those executables, it called a function at 401.724. When we look inside that function, we saw there's a create 232 snapshot to get a list of the processes that are running right now. And then it looped through them using process 32 first and next. If it found the one it's looking for, then it returns 1. And we know that because the checks for 1. Right here on that, there's a test, checks to see if EAX is 0 or not. At that point, we knew that's what it's doing. So we hit F9 again to go back up 1 level. Then we only looked at one more function, the D4C function. But you can tell, even if you set these breakpoints right, and you want to go look at all the other checks that are being made, you can tell that it would actually speed up your analysis tremendously. So we went to D4C. We saw it's calling Reg Open Key, Reg Open Key X. And then we hit F8 a little while just to see what key it's looking for. It's looking for the hardware device map, looking for something SCSI. Then we hit F8 some more. We saw it's looking for VMware, but it was too specific. This is the same problem that all of our signature checkers have. They're looking for things that are too specific, and therefore when a little tweak is made, it can't detect it anymore. We went up back to the very top by hitting F9, or you could follow the steps that are on these slides. I'm not going to go through all of these steps. You can follow these steps, or you can follow the steps that are on your videos. Take your notes. This is why I say make sure you take those notes, because luckily it's on video. You can come back and take those notes if you didn't get them now. That's perfectly fine too. We have one last check at BD6. EAX was one. We don't know what it found. Don't really care, because all we have to do is knock out one instruction, and no matter what it found, it's dead. I keep meaning to tell Lenny about this DW MAPI thing. So it's because actually it's not on the slide here what we would save it as. You patch it, you could patch it, and then we were used to be saving it as RAS patched. And so next time we would run it, it would find the DW MAPI, and so you would have to map out the JNE that was checking for DW MAPI. Now you know all you have to do is rename it. You don't even have to knock out that other JNE. And there's a summary, all the exciting stuff. And you can look at those other functions and see what they're looking for too, and build up a list. Maybe some of those debuggers you've never heard of. I certainly haven't heard of some of them. Maybe some interesting tools you could find out there. So just a quick overview of what we just finished, and then we'll take a break. So lots of things the malware can check for. You can see that it's really almost impossible to come up with a system where if you want to monitor something, it would still be detected. You could, I mean, one of the things that I've tried that sometimes works and sometimes doesn't is just renaming the tools. If the tool is just looking for a name of an executable, rename the executable. However, you can't really rename DLLs. That doesn't work so well. So if it's looking for DLLs, that technique won't work. If it's just looking for executables, you might get lucky and be able to just change those names. We know how to bypass those defenses by patching the code. I don't know any other real option except to patch the code that is realistic. All right, let's take our break. We'll come back and we'll see a couple of samples that lied to us. See you in 10. Hi, Ann.
Hey, Evan. I can hear you.
Yep.
Clear, very clear. Yep.
Yeah. When I finally figured out what DW Mappy was doing, it blew my mind.
I couldn't find a lot of reference online.
Uh-huh. I know. It's like I couldn't figure out. And what was weird is we kind of stumbled across it too, because then we discovered that on my machine, I called it with RAS patched, and some of the students, and I saw the little shield, and I asked some of the students, well, do you guys have the shield on yours? And some of them did not because they named it something else. But I never made the connection.
It's definitely a great discovery. So thank you for that.
Yeah,
I'm going to note that for sure.
it's crazy stuff. Let's see, do you prefer Ghidra over X32 debug for some workflows or vice versa? I'll answer that as soon as we come back from break. That's a good one for everybody to hear. And welcome back. So the question is, do you prefer Ghidra over X32 debug for some workflows or vice versa? Here's my ordinary workflow, my standard workflow. Standard workflow is to first do static analysis with all the tools that we've used on Monday and throughout the week, and the ones that we learned this morning as well. So I'll definitely use those first. I will also do behavioral analysis. I'll run it and monitor it, even without running any debugger or Ghidra, because then I get tempted to start looking at the code, and I want to find out more about it first. I will run it in Wine. Let me show you. I think I already have that link up. Let's see. Yes, I do. This is another resource for you to use. This is malware analysis using Wine. And this is something that I really like. So on your Remnux VMs, Wine is already installed, and that's how you can run my Run SC program, is because Wine is installed. It's a Windows program, but it runs just fine in Wine. But one of the things you can do in Wine is this. Let's say you have Notepad. It can be any Windows program. You can say Wine debug equals plus relay, and then specify Wine, and then pass the name of the program you want to run to Wine. And it tells you all of the DLLs that are used and the API calls that are made. This is really good recon. And out on the right, you'll see there's some return addresses. Those return addresses, if it begins with a 7, those are Windows system function calls. It says that RTL free heap was called from a Windows system library. If it begins with a 7E, it's returning back to a Windows system library. It was not the user code that called it. So one of the things I'll do is I'll do a grep-v, and I'll filter out anything that begins with ret equals 7E. Just filter them all out. 7E, 7F, I will filter those out. So now I'm left with the calls that are the function calls that my user code made, and they will have a different address. This is just an example. A lot of times I see is a 400 something. So now I know what the user code is actually calling, and that's really important because they're getting really good sometimes at hiding where they're calling these functions from. You've already seen some examples of that. We saw that just that last example, it was hard to figure out what was being called because the strings were being decoded at the last second before being used. Imagine that on a large scale where every string was encoded, and none of the static tools will work because it's all being done at runtime using a custom technique. In that case, you can run it through Wine, and it will give you this debug output and show you what is really being called. This is a great technique. It comes from back in 2016. I've been using it for a couple of years just for my own recon. So this would be the next step I take. Then I will use, this is a really long answer to your question, but then I will use a Ghidra and the debugger at the same time. Ordinarily, I start them up at the same time. I don't even wait to run one versus the other. I just run them at the same time and see. And as I use each one, I will flip back and forth between them. So I don't prefer Ghidra over X32 so much. It does give me information that the debugger doesn't, and the debugger gives me information that Ghidra doesn't. So they're complementary tools. I run them at the same time. See, I'm going to actually, Anne, would you also pin that last post I made up there? Thank you. So now you have access to that. It's super easy to do, super fast. You've already got it on your REMNux. Why not use it? And it's free. There's a lot of other ways of doing it, but they tend to be complicated or cost money. So let's see, did I answer all questions? Did that answer the question, Dan? Any other follow-up questions you might have on that? Okay, good. There was also a question that was asked by someone in the class that said that they had to miss out some of the material today, and they're worried about the CTF tomorrow, how much of this shows up on the CTF tomorrow. The CTF does not use the samples that we use in class the first 5 days. There are another set of samples that are in your day 6 directories. They are focused on the techniques. So I would, if you missed some of the material today, I would go back and just review real quickly, just skim over the tools. So at least you know what to look up in the books when you're doing it tomorrow. But I don't think there's going to be much of a problem. The material today is more difficult than the CTF, no question. So don't feel like you're going to be doing a deep analysis. And there might be 2 or 3 really hard ones, but other than that, you're just not going to have that problem. You will be able to move on anyway if you get stuck, because you can always take the hint and answer the question and move on. It is intended not to be finishable in the 6 hours that we do it. So from 9 to 3, minus a few minutes of intro, it's designed not to be finishable. I've seen 2 people now finish it in the last 3 years. So I wouldn't worry about finishing it. I would think about it as you're going to learn a lot tomorrow. Nice graphic. All right. So now we're going to look at malware that tries to confuse us, tries to trick us, tries to mess with our minds, and these so we've got a technique that we're going to be looking up next. We've already seen a push followed by a return. If you recall, that was our 68C3 that we saw when we saw some code injection. I'm sorry, API hooking that the rootkit did. It would change the first few instructions of the victim process function to be a push followed by a return instead of a jump, where that really is a jump. So disassemblers might have problems with that because sometimes the assembly language is not what it's expecting. And so we're going to see some things that will also confuse not just the disassemblers, but that will confuse us. The next sample we want to look at is want.exe. There's very few readable strings. It looks like it's might be a packer. We're going to pretend that we don't know the packer because this technique works for some packers, not others, but we're going to pretend we don't know the packer, but we're going to give you a general technique that will work for multiple packers. I did read an interesting article that said that even if a sample malware has a low entropy, it may still be packed. And if you think about it, you can understand why, because just there might be a blob of stuff that would have high entropy, but what if they mix it in with a lot of stuff that's low entropy, just a bunch of low entropy text? That might bring the overall entropy down to a lower level. So entropy is just another way of getting some idea. If it's high, that's a very good indicator, but if it's low, maybe not. It might still be packed. So let's look at, if I told you I want.exe, this one I do want everyone to have it open. Everyone should have this open in their debugger. I'm going to revert because I've been running malware on my machine. I don't know if you were or not. Feel free to revert your snapshot. Okay. This one is called want. Load that up in X32 debug. If I told you that those first 6 instructions are hiding a jump, would you believe me? This might be something, maybe a good bar bet if you're out with a bunch of techie friends. Even normal programmers might wonder what is going on with that. How could there possibly be a jump when there's looks like it's move, push, push, move, X, or move? Those first 6 instructions. Well, to understand that, we need a little bit of background. So you'll have plenty of time to get that loaded up in X64 or X32 debug. So it starts, then there is a jump in those first 6 instructions. What? And I think someone was asking about this earlier about exception handling. I think it was Nick actually. So structured exception handling, you've probably, if you've used Python, you've probably used try except to handle exceptions in Python. Well, C and C++ have the same concept, but how it's implemented is different. And so if there's an exception handler in a function, then it will, when this function is called, that function will have a little record, a SEH, standard exception handling record, on top of the stack. And that little record has 2 memory addresses in it. This only works for 32-bit code, not for 64-bit code. Those 2 addresses, one of them is a pointer to the next exception handler, and the other entry is a pointer to the exception handler in this function. I should say the first pointer is a pointer to the next SEH record. We'll play with this. So you've already seen FS30. FS30, anybody remember what it is? I've emphasized it a couple times, but what is FS30.2? The PEB. Yep, points to the PEB, the process environment block. So what does FS0.2? It points to the first SEH record in the SEH chain. So you'll have an SEH chain that contains multiple records. So if you have function A, the function A may have a handler. And then function A calls function B, and function B has a handler. Function B has its handler, its SEH record has to point to the SEH record of function A. Then function B calls function C. Function C has its own, has an exception handler in it. And it also has to have an exception record that points to the function B SEH record. And it has to have a pointer to its handler. So this is the handler for C, handler for B. My handwriting is horrible. And the pointer to the handler for A. And FS0 just has a pointer to that first record. All of these records are stored scattered throughout the stack. So if you have a lot of functions calling each other, you might have 7 or 8 of these exceptions involved in the chain. They're very simple, but they're kind of weird and wonderful when it comes to malware. If you want to see that chain, there is a way to do that. You can go down and look in the, you can add a watch entry to see if you want, so you can watch what is in FS0. You can see it here on the slide. It's 19FFCC, and that is an address on the stack. So FS0 will always point to an address on the stack in 32-bit code. And that will always be the most recent SEH record. That SEH record will have another pointer to the, it's a pointer to the next SEH record. We can also look at it. Let's see. You can't see it. There is an SEH tab up top. That actually, I need to report this. That is a slide 99. I just barely noticed that. I've never paid attention to that before. Now that I circle it, I was like, but it's FFE0. No, that's not. So that isn't right. Make a note on your slides. That's not right. I'll report that to Lenny. He fixes these things right away. The address is actually FFE4. So FFE4, if it has FFFFs, that means a -1. That means it's the end of the chain. So this is the pointer down to here. And then this is the handler that it's going to call. So if that function with this SEH handler gets executed, it's going to call that address. It's going to call that function. And this is the end of the chain, but it still has a handler too. And I mentioned this, the bottom one being A, B, and C. If C doesn't want to handle this, an exception, if it says, I can't handle this exception, it will pass it back up to B. If B can't handle it, it'll pass it up to A. And if A can't handle it, Windows will try to handle it. And if it can't handle it, it just crashes the program. You'll get an exception error. So what are those first 6 lines of code doing? Rather than doing it on the screen, let's do it on this. Let's do it on live. See what happens. So we have move EAX is getting an address put on into it. Just press F8 to see what's in EAX. Sure enough, you get that value. It puts EAX on the stack. So on top of the stack, we now have an address. If we press F8 again, what's on the top of the stack now? 19FFCC. That is FS0. That's because FS0 was pointing to the previous SEH record that was at the end of the chain. So what did we just put on here? We have a pointer to the previous SEH record. We have a handler. We have a new SEH record on top of the stack with these 2 entries. That's all it takes to create a new entry. But now we have to update FS0. So we move ESP. ESP is the top, pointing to the top of the stack. So we move ESP into FS0. FS0 is now pointing to the new record, which is 19FF7C. We can look at that by looking at the SEH chain on the SEH tab, or unfortunately, I don't think this is a bug, but I think we need a way to do a refresh in here. It doesn't see that new SEH handler. So what you have to do is set a breakpoint. If you set a breakpoint on 429DHC, so down at the bottom, just type breakpoint BP 429DHC. I set the breakpoint, and that causes the debugger as a side effect to update the SEH chain. So now we go back over to that tab, and we can see that new entry. It's located at FF7C on the stack. This is its handler. This is the next one and the next one. So far, so good. We now have a new SEH record pointing to the previous SEH record, and FS0 is now pointing to the most recent SEH record. So what's happening next? We say F8. We're setting EAX to 0. And then we try to move ECX into EAX. EAX is 0, though. It's illegal to move something into address 0. That is not a valid address. And so it will cause an exception. And when it causes an exception, it will look at the most recent SEH record to find the handler. In this case, that handler is at 429DHC. I already set a breakpoint on it so I could see the handler, the chain in SEH. What do you think will happen if I hit F9? What do you think will happen? Any guesses? What instruction will be executed next after that move? What will be its address? Okay, crickets. All right, let's hit F9 and see. Oops, I already said. Okay, it created, down at that first chance exception, this is another time where I forgot to do my preferences. Do not break. You get some extra exceptions that way. So I'm going to hit F9 again to get past that first chance exception. It wanted to give me the first chance at it. But it goes to that 429DHC. And at this point, why did this sample do this? Probably so we would think it's somewhere else. So that we will start analyzing code that follows that move instead of jumping to here, which is where the code really begins. We're not going to go any farther with this because we have another way to unpack this. We could single step through it all, but we're going to not do that. So let's do debug restart. I want everybody to do this same thing because this is one that I want you to kind of have a feel for. And I'm going to type clear DB. I'm just going to wipe out the breakpoints. So into the breakpoints. There's no breakpoints, right? We want to get rid of those breakpoints. Now we need to know a little bit more about how a program works and how the stack works. Let's catch up on the slides first, though. So we just walked through each one of these steps, which created the new SEH record on the stack and triggered an exception, which caused that address that's in that SEH handler to be executed. Don't forget to set your preferences before you run. And we could single step, but we're just not going to do that after we did that. Once we're on that address, we need to do something faster. It will take forever to unpack if we don't have some kind of a speed up. So I removed my breakpoint. I got ready to go. We're going to do some other steps, but I want to talk more about this theory before we jump into that. Let's open up my Excel spreadsheet. Remember the stack spreadsheet? You don't need to open it, that's fine. It's just quickly give you a visual grasp of what's happening here. As we know from day 2, as the program uses a stack, it's going to call functions. Those functions will call other functions, they call other functions. Every function that gets called is going to use a little bit of stack. So as those functions go deeper, the stack use is going to grow. As they return from those functions, they will shrink back. And they'll keep growing, shrinking, different levels each time. But eventually, you would expect it to come back to the very beginning, back to the original state, the original size of the stack. Because each of these functions is supposed to be cleaning up after themselves on the stack. And so somebody figured out, well, that applies to packers too, or unpackers. As these unpackers are doing their job, they're going to be calling functions. They're going to be using space and then freeing it up and then cleaning up. And eventually, at the end of the unpacker, it should be going back to this location. The stack should be going back to its original size. So that is the theory behind this. What if we could detect when the stack goes back to its original size? The debugger can do that for us. And let's show you how. So I want everybody to follow these steps. We're going to hit F8 twice. Do debug restart. Make sure your breakpoints are cleared. Hit F8 twice only. Very important. F8 once, F8 twice. We just pushed EAX on the stack. Now we want the unpacker to do all of its work, and eventually when it gets right back to this point, we want it to break. We can do a new kind of breakpoint that we haven't used yet. We can set a breakpoint on this address down in the bottom right-hand corner on the stack. Right mouse click on that address. Choose hardware, set breakpoint, hardware access, dword. So I'm leaving that up on the screen there. Right mouse click on that address in the stack, then breakpoint, hardware access, dword. So this sets a new kind of hardware breakpoint that anytime that address gets accessed, stop the program and show me where that happened. And what we're hoping is that that will be at the end of the unpacker. As we will see, there are some false positives, but we will be able to identify those. So go ahead and choose that dword, set that breakpoint, make sure it says hardware breakpoint set at FF80. Now we can run. And well, is it unpacked? How do we know? Well, a couple of things. The first false positive way to tell a false positive is very easy. Look up at the top of the screen. And if you see a Windows DLL, that means it's false positive. It is not done unpacking, because sometimes it might come back to its original position multiple times throughout the unpacking process. And in fact, that's what it does. Or possibly something is reading from the stack. Maybe this NTDLL is reading from the stack. Either way, it says NTDLL at the top. We know we're not there yet. So now you can press F9 again. It changed that location. It still says NTDLL.dll at the top. We have not reached that point yet. Let's press F9 one more time. That's the third time. We're still in that location. We're still in ntdll.dll. Press F9 a fourth time. Now it says we're in 1.exe. Now it's getting kind of exciting. Maybe we're there. How do we know we're done? How do we know if it's unpacked or not? This could still be a false positive. But how do we know? Any ideas? Remember we did this yesterday. We did it earlier again today. What do you see when it's done unpacking in this memory region? What do we see? No one's typing. I'm getting worried. There we go. An MZ header, maybe in the memory. Dan says readable strings. Absolutely. We see readable strings when it's done unpacking. Yeah, we mixed it up a little bit. So we saw the MZ header, the 4D5A, when we were doing other kinds of unpacking. When we were looking at RTL decompressed buffer, or we were looking at write process memory, we were able to go see that it was unpacked because we could see that MZ header. Other times, if we're looking for stuff in memory, we still need to see the other way we did yesterday, more of it yesterday. We did a right mouse click, and we searched for in current region. We look for string references. Well, that doesn't look very good. You could also, I suppose, look in the entire module, see if there's anything. Let's look at the entire module. That's looking at all the memory blocks. As I recall, there's not very much even in the entire module. There's only 3. So not too exciting. I'm going to close those little windows. Don't need those. Go back to the CPU window. So we're not done unpacking. That's how we know we're not done. We found that there weren't any, very few readable strings. Hit F9 one more time. Are we in? Nope, we're back here into want.exe. And just like I did my happy dance yesterday when we found the end of the unpacker, it looks like we found the unpacker here today too. We see a jump to EAX. This is a common pattern. You will see a jump to the beginning of the code. And then you'll also see quite often a bunch of zeros. We saw that in our first in BRB bot when it was UPX packed. This is not UPX, but when it was UPX packed, we saw a lot of zeros at the end of the unpacker. We just found the end of the unpacker, we think. To know for sure, we need to jump to that EAX address, and then we need to dump those strings again. We need to search for those strings. So hit F8 once. Make sure you're careful and deliberate. I've more than once hit F9 by accident. You want to hit F8 to jump to that address. We're hoping that is the original entry point. Looks like I must have missed it. I think you might have to hit it twice. I had to hit it twice on mine. But be careful, don't hit it too many times, otherwise you'll overrun. You'll have to restart. It's not take very long, because then you just restart, hit F9 5 or 6 times until you get to the jump, and then hit F8 once. 5 seconds. It's fast. We hope this is the beginning with the original entry point. How do we find out? We look for those strings in the current region. Remember, it got unpacked into this memory region, so that's why we're looking in that memory, in the current region, not the whole module. String references, yes. Lots of stuff. You can scroll through. Oh, look at here. All your files are encrypted by Lockbit. Current version run. Service is stopped. Kind of get the idea. We've got the ransomware sample, but we've got it unpacked now. We've been dumping out of memory by using the dump windows today. let's go back to the original technique we used yesterday, because we now know the original entry point. So we can then use our plugins, use Ollie dump X to dump the process. And get the EIP as OEP. Remember to fix the OEP. That original entry point must be fixed. Otherwise, it will jump to the unpacking code again when you try to run it. So we're going to get it, and then we'll dump it. Click dump. And just save it on the desktop. That's good. It's going to call it want_dump. We've done this a couple of times. This is like third or fourth time. So that dumped it out of memory, put it into a disk type format. But we still haven't, and we fixed the OEP, but we haven't fixed what? Do you remember what we still need to fix? Anybody remember what isn't fixed yet? We have to run another program, another plugin, the IAT. Yep. So IAT, we're going to fix it with Scylla. So under plugins, go to Scylla. It already has the active process chosen for us. We only have to hit 3 buttons. IAT auto search, and it will ask if the choices are different. Let's say yes, just for fun. It didn't find anything. Oh, well, let's get the imports. Let's see if it worked. Oh, this one works. Okay. This is a brand new sample. We haven't used this one yet. This used to fail. It used to give us some X's, some red X's. So that's fine. We'll just use this one because it's all green. But if it was red, what you would do, I'm going to show you what you would do if it were red. Clear that. There's a little clear button out to the right underneath that box, the imports box. Do the search again and say no, and then get the imports again. And sometimes that will work. So you do whichever one works and gives you all greens. In this case, they both give us all greens, so it doesn't matter which one you do. So do the search, the get, and then fix the dump, which we just saved to disk. Remember, we have to fix what's on the disk. We have to choose want dump, and then click open. And if that was successful, let's say import rebuild success. You should have an undumped program that you start all over again at the very beginning, and that you can run. And we just close out of Scylla. And that's as far as we're going to go with this sample. So we'll close out. But you could take that one dump Sky, put it into PE Studio, do all the standard stuff we've already done. This one, we already know from the strings that it's lock bit. Later, when you have more time, just start up that want dump Sky and just let it run for a little while, and you'll see the ransomware ability. You'll see the ransomware message. You'll be able to revert your snapshot. This is why it's so fun to have a snapshot, because you come up with these messages. The Maze ransomware was a really fun one because I was sitting here watching Maze doing all of its encryption, and all of a sudden, it started talking through my speakers, and it said, "Dear RAM, your computer has been locked up." It was really creepy. It was using that text-to-speech thing in Windows. I was like, and it read the whole ransomware note to me out loud. And my speakers were up to that at the time, so it scared me half to death when all of a sudden it started talking at me. So, yikes. That's a pretty neat technique. This particular packer is called PE Compact. But it will work for some others. That, of course, the people writing packers know that we will use this technique, and so they will also write their unpackers so that they don't clean up the stack, and so the technique doesn't work sometimes. That's fine. We'll just pick any other technique we can find. So we stepped over the first 2 instructions. We needed to step past that first push So we have a reliable, a slightly more reliable place for it to set that hardware access breakpoint. Is that fake jump thing at the top a good indicator for that packer? Yeah, it is actually. And there are tools out there that will try to identify the packer, but like I said, so much of them are custom now that they're probably not going to figure it out. But even some of the custom ones, you could use this technique possibly. So we ran it. We saw some false positives. We saw NTDLL a couple of times. We saw the first hit on want.exe was a false positive because we had to look for some meaningful strings by searching for those string references. We didn't see very many, even in the entire module. Then we saw a jump, and it's really common that at the end of the packer, the unpacker, you will see a jump. So you want to follow that jump, and you hopefully at that point then we'll see the beginning of the code, which is the original entry point. Search for the strings again, and you have lots of strings. At that point, it's time to dump it. We fix the OEP. We then go into using OllyDumpX. Then we go into Scilla to fix the IAT. We could dump it with Scilla as well. You can see there's a dump here. I tend to use OllyDumpX just in case I need to set up any other settings. If you'll recall, we had to use OllyDumpX because we had to change the memwrite on the UPX1 section, but you could sort of use Scilla too if you didn't need to do anything special. It's just that there are more options in OllyDumpX. Vast majority of the time, you don't care because you'll just accept the defaults anyway. Load it up in. I love some of these items on the right. Look what this sample is doing, and this is really common for ransomware. Look at some of the actions it's taking. You can see there's. So this is the sort of thing that you could definitely want to report back. It's calling VSS admin to delete your volume shadow copies. Calling BCD edit to set the recovery stuff. We see, yep, here's some log clearing. More than one, it uses multiple ways. That's pretty sad. Looks like it's trying multiple ways of deleting the volume shadow copies. It tries those WMIC if it can't get to VSS admin. Use WMIC. So these are the kinds of things that you want to definitely be reporting back as items that should at least be monitored, possibly alerted on, possibly removed from the system if they can be. You can't really remove WMIC, I don't think. I might not be able to remove VSS admin, but you at least want to monitor it. So that stack breakpoint technique works pretty well. It's trial and error. Sometimes with these samples, you've seen we've done a variety of different ways of unpacking, and sometimes it's just trial and error. Go through them, figure out which ones work, and if they work, great, move on with your analysis. The next one we're going to look at is really sneaky. Programs all have one main thread at least. So they have one main thread. They may have multiple other threads. Processes don't run, it's threads that run. So a process is sort of a container that holds threads. Many times they might only have one thread, but other times they have multiples. So those threads sometimes need to be able to initialize some data. And so they have what is called thread local storage. That thread local storage is initialized using TLS, thread local storage callback functions. Those callback functions are called even before the original entry point is executed. And so we have to be able to set breakpoints on those TLS callbacks, be aware that they exist, know to set breakpoints, and be able to analyze the code that's in those functions. And so the malware actually might begin in one of those callback functions instead of at the original entry point. Let's take our break. We will come back. We will do this sample, which does just that. You can look at PE Studio. There is a section for TLS callbacks in PE Studio. We are going to remember that address 401031. The debugger will set a breakpoint automatically on it, and we will then look at it. So see you in 10 minutes. Yeah, Nick just counted the samples in the day 6 directory, 26 samples. That'll keep you busy for tomorrow, right? Obviously you won't do a full analysis of all those samples. You're just gonna answer specific questions about them using the techniques and the tools that we've covered this week. And it'll be everything, really. It'll be static, behavioral, and code analysis, all of that, plus some trivia. So you can hear me, Ann?
I was just going to say, I can still hear you. My
Sounds good. And welcome back from break. Wow, we're down, I think, to the last 2 samples. Of course, they're kind of largish. So this next one will definitely take us this entire up until the next break. This is LandServe. These last 2 samples, yeah, I know, right? These last 2 samples, I definitely highly recommend that you watch and take notes. Following along, with these 2 is complex. I mean, there's some interesting, especially this next one, which has some really interesting assembly language code that is very detailed. And if you're not focused on what's happening and you're trying to take notes and trying to also follow along at the same time, it's going to, you go a little bit schizo with that. So I would recommend focusing on what we're doing and my explanations, my walkthrough, and taking notes on things that, hey, this seemed weird, and maybe asking questions as I go along, so that as you see something that doesn't make sense, ask the question. Because this one is a little bit, it's an advanced sample, no question about it. So I'm not going to do milestones or anything like that. This is one I want to walk through, and because I've just found from experience that it's really tough. For everyone to follow along with this one and the next one. And it has just been more successful to walk it through and have more of a discussion about how these next 2 samples work. I'll be watching Slack as usual very carefully. This is a 32-bit program. Actually, you know what? For this first part, let's all do this together. The first part is really fun, and I don't want to ruin the fun by just showing it to you. Let's do this first part together, and then I'll go from there. I think let's do that. So I'm going to post a poll just so I know when you have it loaded in the debugger. So unzip LandServe, get it loaded in the debugger. This first part is really kind of exciting. It's clearly a PDF. I am confused. Oh, from the icon. I didn't even look. Yeah, there it is. Yeah, yep. I should pay attention to the icons. So as soon as you get it loaded up, I think everyone should do this first part. This first part is just way too much fun. Well, we did say the PDF was a payload delivery file, so payload delivery format. I see 3 people have it loaded up in their debugger. Just waiting for the rest of you. Okay, we got 6. That's normally how many I usually see checking. So in this case, I want you to hit F8. Just hit F8 a few times. Don't worry about how many times. Just keep hitting F8. In fact, you can hit F8 a couple of dozen times or even 3 dozen times. Won't cause any problem whatsoever. Even 4 dozen times. Just hit it a few times. Watch what's on the screen. I'll give you a couple of hints. Wrong one. Notice where EIP is. Notice where EAX is. Keep your eye on the lines pointed to by EAX as you hit F8. And then tell me what this little bit of code is doing. Watch what happens to EAX and watch what happens to the code that it's pointing to. Extra points if you can tell me what's happening in the loop. A very tiny loop. It's only like what, 4 instructions? XORing byte by byte, Arun. Awesome. And what is it? And what is it creating? What is it decoding when it does that XOR? The executable. Yeah, it's decoding itself. I love that. That is so fun to watch. You don't, you'll see shell code that does this pretty often. In fact, the shell code that we looked at with qa.doc does this. It decodes itself. Remember, we had the offset of hex 3b. It's that lab, and it actually decodes itself. And you can watch it in the debugger the same way. So I just hit F8 a few times, bunches and bunches of times. So I may have pressed too many times. Well, maybe. Luckily, restart is a thing. You might have to revert. I don't know how far you went on that one, but yeah, you didn't have to go too crazy. No, you can actually tell how far you can go, though. This is another test of our loop techniques. What is the ending condition of our loop? Well, that ending condition is when EAX, as long as the EAX is not equal to ECX, it's going to jump up. So as soon as EAX is equal to ECX, it's get incremented by 1 each time, then it will fall through. So if we look at ECX, it is equal to 40124A. So everything between where EAX is now and where ECX is, it will decode. So that's that block that it's going to decode. We don't want to wait for it to decode the whole thing. It looks like Nick kept hitting F8 until it finished decoding and then some. But what we can do is on that NOP that's immediately after the loop, we can highlight that line and press F4 and watch the screen very closely. When I hit F4 and I hit that NOP, all of a sudden, magic, we have all that code is now decoded using a hex 4D. We see that hex byte right here. 4D is being XORed with whatever is pointed to by EAX. We can also look at the registers. EAX is now equal to ECX. Seeing the PEB. Oh, yes. So Anne posts up here on the 05F. It looks like it's referring to FS30, which is the address of the PEB. Looks like it's also going to follow some pointers in the PEB to get to kernel 32. And we talked about how shellcode uses this technique to find kernel 32 so it can, because it doesn't have an import address table. But even if a program has an import address table, programs might want to use the same technique so that they don't have to use get load library. They can actually go scan kernel 32 for get load library and get proc address, and then they can call them manually. It's a little different technique. So just a little bit of obfuscation there in terms of logic. We're not going to go through everything here. From this point on, this is where I kind of want you to watch now. I just wanted you to kind of see how cool it is to watch the code be decoded before your very eyes. It's like a magic trick. So is the SEH technique, by the way. Now that you've seen it, now that you know to watch for FS30 and for FS0 for the SEH, you're going to notice it. And the debugger helps by showing you FS. So we're going to jump ahead a little bit. We could do this single step at a time. It would just take too long. We don't have that much time in the day. So I'm going to jump ahead to 4011 BA. And that's going to do a call EAX. I'm going to execute until that point using F4. We've done that many times already. So let's go to hit F4 and see what happens there. So it stopped on that 4011BA. This is where I want you to start just kind of watching. Well, that was weird. I guess it filled in the some hints and then decided they're gone now. Oh well. Look at the heads up display. What function is being called? What is an EAX? What function? Yep, is debugger present again? We could use Scilla to fix this, but we want to demonstrate a more general principle, which is that when a program is detecting your tools or detecting the debugger, it may not act on that knowledge right away. It may wait till much later, which makes it much more difficult for you to figure out where that check is. So this is an example that does just that. Let's see exactly what it does. So just kind of follow along, take notes, and this is where it gets a little hard to follow because the code is that way. So we call EAX, call isDebugger present. Yes, EAX equals 1. Yes, we could fix it, but this is just an example of a technique. If it's not isDebugger present, it will be something else that maybe we don't catch or that Scylla doesn't block. So it compares it with EA1, I mean EAX with 1. If it's not equal to 1, it will jump over the add. So EAX will either be 0 or it will be 1. We can look down at the bottom and see that in the heads-up display, the jump will not be taken. It will add A to EAX, so EAX will now be equal to B. And it will put B in EAX. We can see it's in red up in the top right-hand corner. Kind of keep your eyes on both areas as you walk through the code. What does it do next with EAX? Well, the next instruction doesn't do anything with EAX, so we're just going to skip it. We just want to see what's it doing with that EAX. It's certainly not doing a test or a jump. There's no end, there's no decision being made here. So what does it do with it? Skip the next instruction. The next one has no reference to EAX, so skip it too. So it's going to move EAX into memory pointed to by ECX. ECX is equal to 401015. I'm going to put a note in our channel just so I can remember that number. It's going to store it there. That's the important thing we need to know right now. And I'm also going to put a little note, B if debugger present, else 0. So just a little note, because later we're going to need that. We're still in the TLS callback. We haven't even reached the original entry point yet. If we look at the breakpoints, we can see that there's a breakpoint that's already set that the debugger sets for us on the entry point, so we don't have to set it. So when we're done at this point, we're going to hit F9 and go to that entry point. What we've seen so far, the sample unpacks or it decodes a bunch of itself, and then it executes it. That raises an interesting question, though. How would you dump this sample from memory? It's definitely more difficult to dump this sample from memory because this sample only decodes itself a chunk at a time. So yes, it's going to be decoded, but you're going to have to spend the time to find out where it gets decoded and then debug through that code. One of the things you can also do, and let me do this here in just a minute. Let's do run first to get to that original entry point. First thing it does is a jump. I'm just going to hit F8 to do that jump. Hit F8 a couple more times again. Anybody recognize that chunk of code right there, those 4 lines? It's not quite the same because the addresses are different, but it's also decoding another chunk of data. So you see down here, all of this looks like kind of garbage code, a lot of decrements and so on. And we have this XOR with 4D. So, and we see EAX where it's pointing to is right here. So highlight the NOP again and press F4. And it decodes another big chunk of code. So back to my previous statement here. So it does it one chunk at a time. How would you go about dumping this out of memory? Because if it hasn't executed all of its code, maybe some of it hasn't even been decoded. And so when you try to dump it out of memory and run it, if I did it right now, what's going to happen? It'll run that little loop with the 4D, and it will re-encrypt it. If you XOR A with something, it will encode it. If you XOR A with that something again, it will decode it. Yeah, you know what I mean. So if you XOR that something twice with 4D, it just returns it back to what it used to be. A XORed with 4D will be, and then XORed again will give you A. So one possible technique, and probably the easiest, it's still not real easy, would be to maybe patch that XOR byte and change that to 0. After you make sure it's done decoding, what if you were to change it to 0? Because something XOR with 0 is still that something. So that is definitely a possibility. And it's something that I would certainly consider if I thought it was important to dump out the whole program onto disk and try to run it. I would have to try to find all of the loops though. And they may not always use 4D, but I can probably always, if I can find the loops, I can change all the XOR values to 0. Are we good so far? And it's going to be amazing. It takes this full time period just to go over a few lines of assembly language. You're going to see just how intense this can be. What are we looking for next? Well, F8 a few times, see if anything pops up and says, this looks weird. Move AX into GS. Does anybody recognize the GS register? You shouldn't. We haven't talked about it. It's not something a normal program should use. We've talked about FS, a normal program shouldn't be using, because FS is used by the system to point to the PEB, to point to SEH. What is GS used for? I don't even think it's used for anything in 32-bit code, but 64-bit code, yeah. So it's trying to change GS. What is AX, EAX? What is it trying to change GS to? Trying to change it to 53. If it's successful, look what else is 53. FS is 53. So if it's successful, it can use GS instead of FS. So the compiler, the debugger is already flagging FS in red. It doesn't do that for GS. And a lot of detection tools might be looking for usage of FS, not GS. So what if the malware starts using GS instead of FS? It's more stealthy, at least in theory. But now that you've seen the trick, you say, oh, if I see GS or FS, there's something wrong here. Unfortunately, there is also a problem. This is a 32-bit program being debugged in 64-bit and a 64-bit operating system. And so that move statement doesn't even work. It will work if you just run the program, but it won't change GS in the debugger. So you'll see GS is still 2B, not equal to 53. But we know what it's trying to do. And if we want to be successful in analyzing this sample, everywhere we see GS, we have to change it. We have to patch it to be an FS. So I hit the space bar on that line. There it goes. And I change GS to FS because I know that's what it's trying to change it to. Then I say, okay. Now it's in red because it knows that it's FS. Are we okay? Any questions with that? I'm going to make a little more room. Because I'm going to do some drawing here. Oops. There we go. Now we enter a section of code that is another tricky part of the code. We have move FS0 into EAX. So that is the start of the SEH chain that we just talked about a couple of exercises ago. Then it pushes EAX on the stack. Then it does something that we don't care about. There's just another instruction in here that's not relevant to our discussion. It changes EAX, but that's not going to change what we're going to look at. We'll look at EAX again in a minute. But what we do care about is that it changes the top of the stack. It adds 4 to whatever's on top of the stack. And then it pops the result into EDX. What does that do? Remember I said you want to kind of document what's happening here? On top of the stack, which it's going to move the SEH pointer and put it on top of the stack. So on top of the stack is now pointer to SEH handler, SEH record. That's on top of the stack. A pointer to it. Then it adds 4 to it. So skip over the move and go straight to the add. It adds 4 to whatever's on top of the stack. What is that equal to? A pointer that SEH record. Let me just, so on top of this, that SEH record, so SEH record is a pointer to the next record. And then there's a pointer to handler. So this pointer is pointing to this. If I add 4 to that pointer, now on top of the stack, it's not pointing to this anymore. It's pointing to the handler. Okay, so what we're doing is saying on top of the stack now is a pointer to the most recent handler in the most recent SEH record. Then we do a pop. So D, EDX now points to SEH handler in last or most recent SEH record. So what did this end up doing? And just to summarize it, let's just summarize it here. It says D equals FS0, EDX, I should say. Let me go back. EDX equals FS0 plus 4. That's what those lines of code do. It just says, I'm going to put FS0 plus 4 into EDX, or most recent handler. This is a pretty good sign that this is custom assembly language. I don't know of any compiler that's going to use the stack this way, or point to SEH handlers this way, or anything like that. That somebody custom wrote this. It's why it's a little bit more difficult to understand it, because it's dense code. It doesn't do a lot, but you'd have to spend the time to figure out what it does. When I first looked at this sample, it took me a while to figure this out. I did not do this in one go. When I prepared to teach it, I probably ran it at least a dozen times, trying to figure out how am I going to explain this. It's not the most easy thing to explain. But now we know what it does. It's actually something simple. It's just doing a little arithmetic. But now we also know if it's got EDX pointing to that handler, maybe it's going to do something with that handler. Let's see what it does with EDX next. And for that, so we're on this line here. Let's walk through that code. We'll let it do that calculation. And we see EDX gets used immediately afterwards. EDX is 19FFD0. That is that handler. It's going to overwrite that handler. What is FFD0 at the moment? So right now, 19FFD0 is pointing to something, a handler in NTDLL. We can look at the stack down at the bottom. We can see that. And what's it going to put in there? It's going to put 403FEF because that's what is in EAX. So it's moving EAX into that SEH record. We'll see it in just a second as soon as I hit F8. And now we probably have to, I see an EAX. Oh, what happened to FFD0? Went down here somewhere. Here we go. It changed my information on the stack for some reason. My stack scrolled a little bit. So I had to go down to 19FFD D0 to see that 403FEF. We can also set that breakpoint on that. So so that it will update the SEH. So 403FEF breakpoint. Look at the SEH chain. And it used to point to something in NTDLL. Now it points to LandServ. So the next part of the analysis is think about, well, if it's changing the exception handler, maybe it's going to do something like we saw earlier, where it's going to try to cause an exception, and it will try to transfer code 2403FEF to that exception handler. So we're now going to start looking for code in this next part. What could possibly cause an exception? We've already seen if you try to write to a memory address that is address 0, that will cause an exception. What is another way to cause an exception? Another way to cause an exception is to divide by 0. So let's see if we can figure out where that's going to divide by 0. First of all, we're going to look for some moves. Is it trying to move to something that might be 0? So let's hit F8 for a few times. And just to watch each instruction in turn, there's no memory address 0 there, no memory address 0 there. You can look down in the heads-up display and you can see that those are not any, there's no 0 memory addresses there. Again, there's none. Get tick count, just F8 over that. Still no zeros. And this is how I would do it. I'm going to be looking for those zeros. I don't see any. I'll speed it up a little bit. It's going to do a sleep. That's fine. It's not a very long sleep, not a big deal. It's going to do a divide by ECX. Well, what is ECX? Look what ECX is. It's B. Remember where we saw a B? Way back earlier. Yep, 12C8. Yep, thanks, Dan. We saw it there. And just as usual, I also went too far. What I needed to do is say, well, what is being moved into ECX? Where did it get that B from? Well, luckily, it wasn't too far. We don't have to restart because it didn't change ESI. I can click on that line where it last used ECX. I can look at the heads-up display. Look where it read it from. That's the address that I posted in our channel. EDX gets XORed, yeah. But when you divide does something weird. Divide takes whatever's in EDX, EAX, and divides it by ECX. So ECX is the divisor. So in this case, it's actually dividing by B. ECX is dividing by B. That's not going to cause an exception. So it's not going to jump to 403 FEF. Because there was a debugger, it will not cause the exception. Feels like backwards logic. Because there's a debugger, there won't be an exception. And it will do something else. It will mislead us. The real malware is actually stored over beginning with 403 FEF. So to make this happen, you would have to come to this, change ECX, which is equal to B. You would have to change it to 0 to cause the exception to happen. We can do that. I already set the breakpoint. I can say OK. So if I run this time, make sure I set my options. I never do this. There we go. Kind of have to remember to do that. If I hit F9, it will now break on that FEF because I set the breakpoint there already. And sure enough, there we go. At this point, you could then continue to analyze the sample from where it really begins. Here you also, it's kind of cool here too, because you see what is basically an import address table type thing. You can see the functions that are going to be called. You can get some ideas of some other things you might want to set breakpoints on. Whew. Interesting little sample, I think. Like I said, this is one you're going to have to execute multiple times, walk through the slides, watch the video, do it step by step at a time, take some time to understand each step. If you do it both the way I just showed you and what is on your slides, I think you'll get an even better understanding because you'll see it from 2 different approaches. I came pretty close, but I gave you to the slides, but I gave you some other background information about what's going on. So it all started with that TLS callback. You could also see it in Ghidra. You'll see that TLS callback. Here's another case where that doesn't realize that the TLS callback is actually a function, and it doesn't even recognize it as code. So you can disassemble it. And we saw that little loop. You can see it looks like a deobfuscation loop. And that's where I love having every class at least run through that loop so they can see that code be deobfuscated in front of their eyes. Watch it be decoded. It's so much fun. And of course, if you look at it in Ghidra, it can make no sense out of it. Once after you figure out what that range is supposed to be, and you can figure that range because those are hard coded. And this is not in your books either. Look what gets put into ECX. If you can read your loops, then you can say ECX is here. It's going to compare them. And where does EAX begin? Well, actually, it starts. Let me get rid of that one. EAX equals 4015C minus 401038. So, and then it adds something else. So that might be a little bit more difficult to figure out exactly where EAX is. You might want to run the debugger first, but once you've run it through the debugger once and you know what EAX is going to be equal to, which is immediately after that, it really ends up being here. It's where it starts. I know it's weird. Then you can write a script in Ghidra to decode all this data and convert it back into code for you. There are scripts that you can read each byte between that, in that range between EAX and ECX, XOR it with 4D, and be able to see the decoded code. So you could do static analysis in combination with some dynamic analysis to help you out a little bit. But until you do that, the decompiler won't make any sense out of it. If you run a script to decode it, then the decompiler will do just fine with it. That, of course, is a more advanced topic. It's not in the class. The debugger automatically stops because we set this checkbox for you in the VM to automatically stop at any TLS callbacks. That it automatically creates breakpoints there. I finally did remember to set those options. And because this takes too long to single step through everything, we jumped right ahead to 4011BA because we wanted to show you what happens if there's a delayed reaction, a delayed response to something that the malware doesn't like. Oh, you'll notice in this case, there is a set hardware on execution. And that was necessary because that is being overwritten. If we had put a software breakpoint there, it would have a CC. It really didn't affect it because I executed to the end of the loop, to after the loop, before I set the breakpoint. But if I had restarted, I would have to do that same thing. So if a hardware breakpoint here means I could restart the program without having to, and then immediately hit F9, and it would stop here. Let it do its work, and it would automatically stop here. Very much like what we saw with the other unpackers. We saw the call to isDebugger present, and we walked through that code one step at a time in the debugger so that we could check that if there is a debugger, it will put a B at address 401015. Otherwise, it will put a 0 there. Then we ran it to the entry point, and we hit F8 for a few times. We saw there was another one of these little loops to decode more code. And just a few instructions later, we saw something really suspicious trying to change GS. And because we're in the debugger, we could tell that it was trying to, well, we could actually even tell here. We didn't, even if we didn't know what AX equals here, because we saw a GS0, we would start thinking, maybe it's really trying to use it like FS. That would be a guess in static analysis. In the debugger, we could confirm it because we saw AX is equal to 53. Then we executed the code until we got to that point. We verified that 53. And then we changed GS to FS. And then we looked at that strange code, that those 5 lines of code that changed EDX equal to FS0 plus 4. And since we walked through that step by step, I'm just going to move along, because that's these slides 130 and 131 go into that in great detail in the same way. And it talks about how EAX now contains that address of 403 FEF. And when we did the pop, that's what, there's a 132 talks about that structure of that SEH record on top of the stack. And I already documented that for you as we did at 5. Now EDX is going to be popped up and point to that. So the debugger confirms that EDX points to the handler. And the very next instruction puts FEF into that memory address. So it changes the handler. Deep waters. So this sample did not create a new SEH record because the author of the code knows that we're looking for that kind of behavior. So it changed an existing handler to point to its own handler. And then it caused that exception, caused that divide by 0, only if the debugger is not present. We had to do a little bit more checking here. We had to look for something that might cause an exception, which was that divide. And we went to that instruction, says, well, what's in ECX? I clicked on that move, and the little heads-up display showed us that it read 401015, put that value into ECX, which was a B. Sure enough. And if there were no debugger, it would be a 0. And we covered all that. And so we could have changed ECX. In fact, I did change ECX to 0 so that we could cause the exception, so that we could then continue on with the analysis if we so desired. We're not going to go any farther than this with this example. But now you know how you would walk through it. You can tell how some of these samples may, when you start getting some of these more sophisticated malware samples, you may be spending quite a few hours figuring them out. And maybe some of them will just be too hard. That's why I was asking the question the other day, when do you decide that malware analysis ends? You may decide that this one is just so difficult. Maybe you're going to settle for just running it in Wine and collecting all the API calls, coming into the debugger, making sure you have Scylla loaded, so at least you can have as good a chance as possible of success. Set breakpoints at the key places so that you saw in Wine, or that you saw with Kappa or any of our other tools, the import address table. But sometimes you may just have to say, well, I'm going to get as far as I can, and after that, I'm done. Sting used to say that you never finished making a record, you just abandoned it. Same thing here. Yep. Yep. Yeah, that is sort of the feeling. You're going to run out of time or money, and sometimes you just have to quit. I never did finish working through Maze. I spent about 3 weeks total on it. And I still want to go back. I still want to figure out how to write some scripts that will deobfuscate all of that code. I need to go back and review some of my computer science stuff, and actually take another computer science course specifically in this area so that I can write that script. I'm not at that point yet. That's heavy duty, master's or PhD level computer science stuff. Heavy duty to try to do that. If you allow it to keep running, you would see that it's NanoLocker. I'm sure one day you'll get out of that maze, Evan. Ooh, yes, true. I will. I'm going to take some time off, actually. At the end of this year, I'm going to take a couple months sabbatical off. And that's one of the things I plan on learning. I might even take 3 months off if it takes too long. So I'm really, really excited actually to do that. It's one of the more exciting things I've been learning recently. If I can write that script for Maze, it means if I can figure out a way to also make it a little bit more generalized, it should work also for other malware samples. Basically in Maze, you can't find any functions because they converted all the functions into one big, huge function. But there are ways of reversing that, even in an automated way, so they can be reversed, so you can create those functions and be able to analyze that a little bit better. That's my goal. I know it's possible, so that's something I want to do. Kind of a researchy type area, though. Wow. I love that sample because there won't be anything like this tomorrow. In case anybody's freaking out and think they have to worry about something like this tomorrow, don't. You need to know, though, some of these tricks, especially to watch for usages of FS and GS and TLS callbacks and SEH and the PEB. You now have some more things to be looking for that you didn't have before. It's time for a break. Is everybody ready for a break? I am. Let's take our break. We'll come back and we'll do our last sample. We'll finish just a few minutes early. And if you would post the eval if you didn't already. There you go. Thanks, Ann. And we'll talk to you in 10 minutes. Hi, Ann. I'm back from break, just doing a sound
Yeah,
check.
yeah, I can hear you well.
Daily evals, fulfill your destiny.
Stole it from Sam's. We have another channel for moderators.
Yeah, there's a lot of those. Some of them are actually kind of cute.
Sorry, that one was a little scary.
Yeah, that one's not cute. Some of them have cats, I think, cute
Oh,
cat pictures. I don't know if you've seen all of them or not.
no, that's the first one I'm seeing.
Oh, yeah, there's a whole bunch of them. I don't know where they all are. I know the instructors have them somewhere, but in one of our instructor channels, but I don't know where it is for sure right now. It's not like I need another Slack channel. I have
All right.
I have 9
Oh, geez.
SANS related Slack channels. That's crazy. Because a lot of the classes have their own Slack channel. We don't have one for this class. At the end of today, I'll show you what we do for this class. Much easier to manage. One more, just one more example. So I think, Nick, you were also, you posted up those items that API calls that I look at first. Most of them are here on this slide, on slide 144. So if you want to have another reference, it's right here. I think there were a couple of them that I mentioned before that are not on this list though. Think about all the different ways we've unpacked samples now. Well, UPX was easy. We just found the end of the packer and found the original entry point. We did the stack cleanup and reuse. We did that just a little bit ago. Write process memory, RTL decompressed buffer are both very good. We're going to see another one here where it's a little bit trial and error. And when we're done with it, I'm going to also give you some ideas on speeding it up even further. So sometimes you have a sample that is, well, they like to hide things, right? And this one is, the thing that they hid is so stupid that if they hadn't hid it, I would never have seen it. I would never have paid any attention. I was, oh, they're not hiding anything. But because they tried to hide it, it draws our attention right away to the problem there. That's just their mindset. They've got to have this deceptive mindset, I guess, to write malware. This one is called YEP, yep.exe. This is the last one of the day. And it's again, it's another one that, because it's a Friday afternoon, late Friday afternoon, and I know everybody's kind of overdosed on malware and assembly language. I kind of think it's not a bad idea to kick back and watch the same way as the previous one. It's not as complex as the previous one. It's a little bit more relaxing, but we have a couple more techniques for you to learn. And it might be better for this one just to take some notes as I go along. It is also a 32-bit program. So X32 debug. Oh, in my notes, it tells me to remember to let me just see if ASLR is on it. My notes tell me to, but I thought we turned it off. Let me make sure. Yep, it's already off. So I don't need to change it. What slide are we on? Ah, yes. Let me find out. I think it's on slide 140 something. Yeah, we're on slide 145. 146 is where we load it in the debugger. But we also do a little bit of recon that I'm going to show you right now first before I go back to the debugger. No problem. Yeah, I understand work is definitely an issue. I've taken classes where I've had to do the same thing, and then you're playing catch up. So I definitely feel for you. Yep. Yeah, I'm familiar with them. I actually get emails from them. There was a question, I think. No, I answered, no problem. I'm way more exciting. Well, thank you. I appreciate that. So I'm going to drag and drop it onto PE Studio first, and let's just take a look at it. And this is kind of a weird one because it's not something I would look for right away. It's something that if someone hadn't pointed out to me, I would never have noticed it. I need to wait to see the import libraries. I want to see the libraries. There we go. So it uses 4 different libraries: user32.dll, kernel32, compcontrol32, and shell32. What we're going to watch is we're going to set a breakpoint on the load library call so we can see what libraries it's trying to load. I quite often will set breakpoints on load library and get proc address because that gives me another clue as to what functions it might be trying to hide from me. And a breakpoint on get proc address tells me immediately, here's the functions it's trying to find the addresses of that it might be calling, that it might not be in the strings, might not be in the import address table. So we found out that this is calling it's loading 4 DLLs explicitly loading those 4 DLLs. But we're going to see that it's going to try loading another DLL. Why it's trying to hide it from us, I don't know. So that's load library A is what it's calling. I could have looked at that in PE Studio, but EP load library A. This is not something I would go, this is not a technique I would use right up front. I would wait and I would see if it's and I'm a little bit more desperate, shall we say. But at the end, I will give you another technique that is included in this technique that will work more often for you. So I set the breakpoint on load library and just press F9. Load library, we can look down in the bottom right-hand corner, see what the address, see the string that's on top of the stack. It's trying to load kernel 32. Was that in our list of 4? Yes, it was. It was kernel, user, comp control, and one other one. Kernel again. Shell 32, that was in the list. And TDLL was not in the list, but every program uses NTDLL. So that one is a false positive. You don't worry about it. And now we see MSBCRT down the bottom right-hand corner. Why did they try to hide that? That's a Microsoft Visual C runtime library. Tons of programs use that. There's no reason to hide that. So why would they do that? Because they're calling some function in that DLL that they don't want us to know that they're calling. And therefore, they didn't want it to show up in the import address table. So we use that as a guide. Well, load library isn't exactly exciting, but there might be some code close to it that is more exciting. And that's what we're going to go find. Let's right mouse click. I clicked on call stack. Right mouse click. We've done this a number of times already. Follow to. We need to do the follow to because that's where it's going to return to. Scroll up one line or two, and we see, yep, there's the call to load library A. Back to our situational awareness we covered on all the way back on day one. We now want to see what other calls are being made and if they are interesting. It's a little hard with this one, so we're going to have the debugger do some of that work for us. First of all, we have to get to this part of the code. So right now, all we did is navigate. We haven't actually executed to this part of the code. So I'm going to highlight the line after the call to load library and press F4 to run to this line of code. So press F4. We're now in a place of the code. We're going to let the debugger help tell us what else is interesting in this information. So this is a new technique that we haven't seen yet. We have a plugin. You can see there's Xanalyzer is a plugin here, and it will do some other analyses. You can right mouse click in that empty space out here. Click on Xanalyzer is another way to get to it. But you'll see there's some different options here. We want to analyze, and we're going to analyze the module. Let me just double check that that is the right one. I'm trying to remember if it's got to be the module. So we'll analyze the module. And then over in the locals, so I switched windows down the bottom left to show locals. That shows us some of the things that are on the stack, some addresses that might be there. One of those is virtual protect. We talked about memory sections. They need to be marked as executable. And I talked about the technique of allocating memory that is just readable and writable, but not executable, putting the code in that block of memory, then using virtual protect to mark it as runnable, to mark it as executable. So that's where we're going to go. We're going to look at any calls to virtual protect. Virtual protect, to me, is higher priority than virtual alloc. It's right up there. I don't say one is a lot more important because it's right up there with write process memory and some of those others. But virtual protect is really high. So I set a breakpoint on virtual protect. We want to be able to call it from wherever. We want it to stop when, no matter where it's called from, we want to stop at virtual protect. Now we want to run, see what we can see. I hit I clicked the little blue arrow, but you could hit F9. Virtual protect. Now we want to see, well, what is at that memory that it's trying to protect? And what kind of parameters are being passed to it? Virtual protect, the address is, now I'm going to skip going back to the documentation. Again, just a little bit of laziness. But if you look at the documentation, you will see the first parameter is the memory address that is going to be protected or changed. So I want to see what's in that memory. So I follow that in the dump. I follow it here in the dump. And we found another executable. However, this one is a little bit different. This is a little bit different. The second parameter is how much memory am I going to mark? Am I going to change the protection on? It's going to change 4K. So 1000 hex is equal to 4K. That means it's really only changing the header of the PE in memory. It may not actually be done doing the unpacking. I think somebody in one of my classes says that, yes, you can dump it at this point, but we're going to pretend that you cannot, because you need to know how to handle a situation where it's not done unpacking. It's only done the first chunk. And all it's done at this point is we're going to pretend all it's done is the PE header. The other thing we find out is it's marking it as a 2. For that, I am going to go to the documentation. Because I want to show you how to find those memory. So that's the new protect, those protection constants. They aren't actually in the virtual protect documentation. You have to go to the parameter description. And there's a little link right there in that first or second sentence, first paragraph, that says memory protection constants. We scroll down to the constants, we look for 2. We saw that back in the code, we saw that it was changing it to 2. What is a 2? It's read only. So if it's using that virtual protect to change it to read only, that becomes not very interesting. We are interested in something that's executable. So if we look up here, the execute bits are page execute, which is just a 10, execute read, which is a 20, and the execute read write is our friend 40. So now you know how to find those memory constants. This one is a 2, so it's being changed to just read only. We're really looking for some executable code. Maybe it's not done yet. One thing I see fairly often is it will call virtual protect multiple times, and it will mark different chunks of memory as read only or read only execute. We're going to wait and see what we see. So we're watching this code, but we're going to let virtual protect finish. We're going to let it run another time. So let's see what the next block of memory is going to allocate or going to protect. Let's hit F9. Okay, it did it very quickly. You may not, if you blinked, you missed it. It's changing an address at 401000, not with 4 with a bunch of zeros after it. So it's actually the next chunk of memory. It's doing 8K of memory. It's modifying the protections on. It's changing it to a 20. That 20 now becomes very interesting because the 20 says execute read. It's not writable, but guess what that means? It's probably, when it's done marking this chunk of memory executable read, it's probably done unpacking because it's not going to, because it marked it read only, it's not going to be writing into that memory anymore because it can't. It says it's read only now. So I'm going to follow that. Let's follow that memory address, follow that in the dump. This is going to show some junk. If you were to follow it in the disassembler, what you would see is that that is actually code. When you see a 55.8b and so on, it's actually code. Why not do that? Let's show you that. Let's follow that in the disassembler. It's not in your books, but you can see it's actually functions. Get module handle, get proc address, some other stuff. I'm just showing you that just for curiosity's sake. Press the star key or the asterisk, and it takes us right back where we were, just to prove to you that that actually is code. It's not done marking it as executable. And so we're going to wait until it's done marking it as executable. And I'll show you why. In this case, I want to do a debug, execute till return. We want the virtual protect to finish doing its job. And then we're going to say, I want to set a new kind of breakpoint. I want to set an execute breakpoint on that chunk of memory beginning at 401000. So we execute till it returns. Now virtual protect is finished. Now it is safe to set that breakpoint. The right mouse click on that 55. There's our breakpoint. We're going to set, now we could set a hardware breakpoint. It's a little bit hit or miss when you set a hardware breakpoint because a hardware breakpoint is set on a specific address. It will set it on that address 401000. It won't set it for that whole memory block. If you want to set it for the entire memory block, we don't know what part of the code is going to be executed in here. Maybe it will execute a function that begins at 40100, maybe not. We want to make sure if it executes anything in that block of code that we stop. So we have to set a memory breakpoint here. We could not set this before Virtual Protect was done. And the reason is that when I set a memory breakpoint, it changes the memory protection bits. And if I change the memory protection bits and then Virtual Protect runs, Virtual Protect will undo what I just did. So again, if I change the memory bits, the protection bits, using this memory execute single shoot, Virtual Protect will undo that breakpoint that I just created. So I change it to single shoot. I only care one time. We now have that memory breakpoint set. It's kind of like a software breakpoint. Now that it's set and I'm sure Virtual Protect is done, I can run one last time. Oh, I have my Virtual Protect still set. I didn't undo the breakpoint on Virtual Protect. There was another Virtual Protect in another chunk of memory. You can see it begins at 403. It's another different part of memory. It's marking it read only. So that's fine. That doesn't hurt us. We were more interested in the Virtual Protect that changes something to be executable in some way. So I undo that breakpoint, press run. Down at the bottom, it says memory breakpoint execute. And the address it broke on is 402.267. We were pretty sure that it was safe to dump it after Virtual Protect was done. But if you want to make extra sure that it's safe to dump this memory, you wait until something is being executed out of that memory, because then you know it is, you know for sure it's done, because, right, it can't execute unless it's done. And now we're ready to dump it. We'd use the same technique that we did before. Right mouse click in the dump window, follow it in the memory map, right mouse click on the gray bar, dump memory to file. We'll put it on the desktop. We'll call it yep dumped, yep_dump.exe. We're doing good. Leave the debugger open if you're following along. You will need it. And I've already got my command prompt open. So we now have it dumped. We don't, this pattern where you see multiple chunks of memory that are contiguous with each other, the 400,000, the 401,000, 403,000, where they're contiguous with each other. This is a pattern that's common when the program has its own loader. And it's putting the code in different chunks of memory and marking them with the appropriate protection bits. And so when I dumped it out of memory, it's really in a format that is more suitable for it running in memory, not for being stored on disk. And so with this sample, we need to do a little bit more work. And this is on slide 162. A program written by Hasharazad, and I mentioned her earlier. I follow her on Twitter. And she has an awesome GitHub repo with some great tools. We use one of her tools, PE Unmapper, PE_Unmapper. And it converts the in-memory format and moves things around a little bit so it's more appropriate for an on-disk format. We put /in, yep, dumped, and I guess did I make it underscore? Yeah. Just make sure you use the same name. On your slide on 162, it says yep --dump, but I always use underscores. We give it a base address. What is that address we used? Go back to our, oops, if you just go back to the debugger. That base address is the same address that we dumped out of the memory map. So that base address has to be 400,000. I know the code started at 401, but the PE header started at 400. So that base, we're going to put 400 and then 3 more zeros. So a total of 5 zeros. We give it we save it as an out. So we'll call it yep dump fixed.exe. So it should be fixed. It's not quite ready yet, but it's going to be close. But now at least it's in a better format on disk than it was. So we save it. Looks like it's no error messages, so it must have worked. So excellent. And now we yep dump fix. What isn't ready yet? The import address table still has not been fixed. So we go back to the debugger, do our plugins, do our Scylla, do our search, do our get. Oh, we do have some red ones here. Awesome. So we have some red ones here. We can say clear, do our search again, say no, because the advanced search returned us back some red errors. So click no. So we use the standard search, we get the imports. Now we got green across the board. We're in great shape. Now we fix the dump. And we fix that one that so we fix the fixed version. So it's yep dump fixed is the one we choose. That's when it's in the most correct state as of right now. We're going to fix the import address table in it. Click open. It says import rebuild success. We should be able to close the debugger now. We should be able to run yep dumped that last version and see if it works. So cross your fingers. This one is a little twitchy. If you miss any step, it won't run. So let's look at it in Process Hacker. And it will corrupt memory to the point that you do have to revert to your snapshot to do this exercise again. So yep dump fixed _ sky is the one I want to click on. Just double click on it. And if it succeeds, you'll see it loads itself into memory as SVC host. Wow, we did it. You could double click on it, watch it, look at the memory, look at the strings of our usual stuff. You see some WinHTTP calls being made. And you start all over again. Now you've got something that's unpacked and is usable. These techniques won't work for every sample. Let's do a quick review of what we just did, and then I'll explain what you do for some of these other things. So we have yep.exe. We discovered that it's trying to load a DLL that's not listed in the import address table. So we set a breakpoint on load library until we found the MSVC RT being loaded. And that took us close enough that together with the X analyzer, we will just see, oh, it's calling Virtual Protect. Yeah, let's do this. We follow those instructions. We could single step looking for interesting stuff, but again, we want to be a little speedier than that. And so we use the X analyzer to find that it's calling Virtual Protect. We set a breakpoint on it, execute to Virtual Protect, and then we watch that first parameter in that dump. And we see, MZ, maybe we can dump it right now, maybe not. Sometimes it's not done unpacking, and that's why if you see multiple calls to Virtual Protect, you might want to hold off because you might want to wait until it's done doing that work. it is changing it to just a 2 to read only. That kind of implies to me that it might not be done yet. Because when we see the next one, and we've had this discussion already, when we see the next one, we see it changing to a 20, which is an execute. And then that's just that discussion we just had is on 155 and 156. We want to make sure that it's done. And we want to make sure the virtual protect is done with that chunk of memory before we set an execute breakpoint on that chunk of memory so that virtual protect doesn't undo our breakpoint. And so we went to that virtual protect the second time. We saw the page execute read. We follow that memory in the dump, and then they debug execute till return till that virtual protect finish. Now we can set that memory execute single shoot safely. And then we allow it to run until that breakpoint, that memory breakpoint gets hit. And now because it's actually executing code in that chunk of code, then we dump it from memory using the memory dump and the memory map that we've done several times before. And then to make sure it's in the correct format, that it's in a disk format, we run PEN mapper, and it will modify whatever addresses it needs to be modified on disk. So when it loads it in, all the sections will be loaded in the right place. We still had to fix the import address table though. Standard stuff. And when we run it, we see SVC host. So you've seen it twice now. You've seen me run through it live. We've gone through the slides, and you're going to have to work through this one multiple times, I think, before it really clicks. Malware authors also try to figure out what we are doing. They know we set software breakpoints. So what if they load the first bytes at the load library A? If we set a software breakpoint, there will be a CC at that first instruction in load library A. So they compare that first byte with CC. If it's equal, then it jumps to another address, which is D35. Where's D35? It's right here. It's doing D35, which calls read timestamp counter. This is not from YEP, by the way. This is from something else. It reads that timestamp counter, and the timestamp counter gets put into EDX and EAX. So it just pushes and so EAX is going to be some random nanosecond type thing. And so it pushes that value on the stack and then does a return. So it's going to return back to a random address and crash the program. So if it detects you're using software breakpoints, then it will crash. There are also ways of detecting hardware breakpoints. There's a variety of different techniques that people use. It's a cat and mouse game, and we just do whatever we can. So there's a walkthrough of that code. So that is the last sample we're going to look at in class. You've got many more tomorrow, and you'll use everything we've learned this week. Won't be as hard as today, I promise. And you'll have a lot of fun, and you'll learn a lot tomorrow. I'll do the demo tomorrow. Let's see. I did post the link earlier. Let's see. Let me post it again so that you have that. Let's see. I posted it to Anne this morning, so she could be my guinea pig. There we go. Copy and paste. Let's paste that. So before tomorrow at 9, please make sure you are registered for the game. Let me see how many people are already registered. Looks like we have 4 people registered so far. So if you're going to be here, please register. And you'll go through this username and password to get past the HTTP basic auth. Then you're going to click register, create a username and password. If you want to be anonymous so people don't know how you're scoring, that's great. That works fine for me. Just don't, just nothing. Everybody will see this on the scoreboard all day long, so nothing rude or anything like that. That's fine. And then think of all the things we did this week. I expect it to take another I expect it to take another 4 to 6 weeks to digest a lot of this. We give you as much as possible. You also have the MP3s. Make sure you download the MP3s from your portal. And you've got your books. So with together the books with the MP3s, it's like you have really a permanent copy of the course. So and it is Lenny's voice in the MP3s. The videos here, you only have access for 4 months. So take the videos and things that I say that are not in the book, you might want to take notes on. And that. So funnel of fun. Today we hit the peak of that funnel of fun. We hit that level. So that is awesome. Here's what we do. You will automatically be registered or added to the REM alumni mailing list. We don't have very many posts on there. Pyramid of Pain. No, 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 no. It's so much fun to do things other people can't do. So much fun. So we do share tips on there. We share samples sometimes. Sometimes somebody asks for a sample and maybe we can get it, maybe we can't. We never know. So after the class is over, I actually send an email to SANS to add you to this REM alumni mailing list, and you get added automatically. If you do not want to be added, let me know. But it's very low volume. It's never cluttered up my email, and it's high quality because Lenny moderates it. He doesn't let any junk get through. So we don't let just anybody get on here. There's also some Facebook links there and Twitter. You can watch those too. Realizing I'm the only one not on the CTF scoreboard. Oh, really? I see 1, 2. Yep, people are getting added really fast. So let's see, 1, 2, 3, 4, 5, 6 so far. I'm on there as the instructor, but I don't think instructor shows up for you. So good. I think we're supposed to have 9 in class, but I know one person is not able to attend. If you have on demand, you will have something almost identical. You'll have access to it for 4 months. So you'll be able to go through all these samples and play with them. I'll be here for another 20 minutes until the official end of class, answering any questions. If you have questions about the CTF for tomorrow, I can answer those now too. If you have any questions about anything we've covered in the class, I can also do that. I hope you've had a good time this week. Thank you for being in an interactive class. It is so hard to just teach without the interaction from the students, because it's like, are people there? We hope you are. Yes, we start at 9 a.m. tomorrow. And so thank you. It's been a fun week. I love teaching these topics. I love the fact that I'm teaching this version of the course for the first time, because we have new samples, we have new techniques. Day 3 was completely rewritten. Want.exe is new today. Some of the suggestions I've had for the class have been implemented in the class. It's kind of fun. We've got Run SC. I'm so excited about that. 0600, yeah, right. It would be nice if you show up maybe 10 minutes early just to make sure everything works and that you're logged into the system. But yeah, Nick, you can show up. You just won't be able to see any of the questions. I will open the game. I will do a quick intro. Read section 6 of your workbook for hints on strategy. There's approximately it's not an even number. It's like 2,600 or 2,700 something is the maximum number of points. Like I said, though, it's not intended to be finishable in 6 hours. The only people I've seen finish it are people that are programmers, really. So I still see only 6 people registered, so maybe that's all we'll have tomorrow. But yeah, thanks, Dan. It's been really fun for me too. I love this topic. You can probably tell that I really get into this stuff, and I love sharing with people, because the more people know this stuff, the faster we're going to shut some of these guys down, and the better our security will be overall. I think we're not at the point yet where we're taking the information that we get from the malware and really implementing defenses the way we should. I think we need to do a lot more there. Oh, and go ahead and I was just about to ask you to do that. Put that up. But thank you, and thank you for the comments and the evals and the compliments that you've given me. I really appreciate that. Does my heart good. Same as yesterday? Sure, Nick. Why not? Last eval is much more detailed and thought oriented. That is a comment from somebody that has taken a SANS class before and knows that that if you want to, if you see something that can be improved, then you put a comment on the specific day. But after that, just just check the boxes, and then on the last day, just that's when you put your comments, if you have comments, and that sort of thing, that overall for the class. Yep, I do the same thing, Nick, actually. I'm too lazy to fill in comments every single day, but unless there's something I really feel needs fixed, then I put it on. And I think I've taken over 25 SANS classes now. I've taken a lot of classes. I love them. Of course, I cheat a little bit because we get them free as an instructor. So I think I've averaged about 4 per year since I became an instructor. Some of them I take more than once. If I hear there's an update to a course, I'll take it again. So that 25 does include some duplicates. I've I like taking some of the pen test courses because that really reinforces the techniques that I see in malware and forensics. Yep. See you later, Nick. See you tomorrow. Yep. Don't worry about that leaderboard. Don't worry about the coin. Oh, I have to tell you this story before you leave. You have to hear this story. This is the craziest story. I had a class, it was a 504. So the final CTF is by teams. And in this, one of the teams, there was a guy that wanted the coin so bad, and his team did not win. And he was so upset that he picked up his bags, kind of stomped to the back of the room, opened his bag, and he had a rather large backpack that he brought to class. He took his arm and scooped all of the snacks into his bag, closed his bag, and stomped out without saying a word. It was unbelievable. All the students are watching me to see how I'm going to react. All I could do is shrug my shoulders. It's like, Nerd rage. There we go. Unbelievable. I thought, dude, you came here to learn something, right? But he was already gone. Un- I told this to the other instructors, and they're just like, they've never seen anything like that either. Unbelievable. That was the last story for that you had to hear about the coin stuff. At least it was just the snacks. That's right. Oh, well, the other part of the story is that he was very, very large. So yeah, it wouldn't surprise me if he rage consumed the snacks too. Wow, unbelievable. Yeah, yeah. You're bummed when you don't win. I came within 7 points of winning a coin, but I learned an awful lot. This was the 5:30. It's the oh, I'll remember it. I can't remember the name of the class. Sec 5:30. Let me just quickly go Google on that. Defensible security architecture. Yeah. And I came within 7 points out of like, I don't remember how many. It seems like a lot of points. Science challenges, whole different ball game. Yeah, they're hard. Yeah. Thanks, Robert. Enjoy. I'm glad you enjoyed it. I'm glad that you feel that I'm patient. That's something that I work on a lot to make sure that you don't feel like I'm speeding through the material. And I like going at a speed where you have time to absorb and do that. 4526 coin by 1 point. Oh yeah, I know. Yeah, that course doesn't exist anymore. And a lot of that, I think, that's the memory forensics class, 4526. I think some of that is because the focus is moving towards doing live memory analysis. I think somebody is working on a course that is related to that. Uh, I don't know if they're actually making any progress on it or anything like that. It's still a lot of researchy type stuff and and a lot of work because Microsoft keeps changing how things work, and every single version of Windows has a different memory layout. And memory sizes are getting so large that it really has to be sort of the memory analysis equivalent of using CAPE, Eric Zimmerman's CAPE for disk analysis. We need to start being able to focus in on those things that are the most useful to us. And that can be difficult. So there's a lot of work going on in that area. I know the guy that was working on volatility, that's his primary area of focus now. Yeah, I took 526 on demand like a month before they canceled it. And it was because it wasn't canceled just because of that. It was because that instructor actually went on to do their own thing. They went on to work on their own stuff and just didn't have time to keep up the material in the course anymore. Yeah, Velociraptor, nice tool. Yep. Velociraptor and Cape, great combination. Did I see that Eduardo got second place in the VR competition? No, I didn't. Cool. All right. See you, Jason. Yep. My, I have no more funny stories that I know of right now, anyway. It'll be on the video anyway if it's in the next 7 minutes. Actually, tomorrow you guys get to do all the work. I just basically handle any tech support. I can't give you any hints because the hints give you the answers already. But I can provide tech support. No problem with that. If your VM doesn't work or something, I'll help with that. Oh, nice. Yeah, Eduardo, he's pretty darn good. That's cool that you get to work with him. It's interesting that the student that figured out what the BRB bot file and conf commands did was also named Eduardo, a student in Munich, and he has like a PhD in mathematics. He's really, I don't even understand any sentence he says when he talks about math. It's kind of hopeless. And I've taken several years of calculus, and his stuff is so far beyond what I can even imagine. Yep, never stop learning. That's the whole thing about this whole field in security, is that you'll never stop learning. If you like that, this is the field to be in my opinion, because it never ends. I'm taking I just finished one SANS course. I'm taking another one. I'm taking the management strategy course. I know I thought I would never take a management course, but I decided this one was worth taking. It's pretty good. And before that, I took the two of the cloud security courses. By the way, the ransomware course is getting close to being released. It's going to be a 4-day course on ransomware. It's going to be kind of a combination of things. So a little bit of malware analysis. The author is Ryan Chapman. He's also a 610 instructor, but he works with ransomware companies to get ransomware all the time. So he's focused on that. So there's the business aspects, there's the forensic aspects, and some of the malware aspects. So it's kind of a combination of things. 710 is getting closer. In fact, while you guys are working on the CTF tomorrow, I'm reviewing the day 2 labs. 710 is only going to start out being a 2-day course, but I'm reviewing the day 2 labs and providing feedback to Anuj. They're in almost finished format, so I'm just doing sort of like the final review and saying, here's what can be improved. A little bit on the typos, but more about the approach. The course code is going to be 528. Let me double check. I already have my SANS. Yeah, it's gonna be 4528. Yep. 45710. Grem 2, the return of Grem. Yeah. Oh, it's already on the SANS website. Cool. Yeah, I think I don't know I don't know the schedule at all. Does it have a schedule for the beta coming out? I'm gonna click that link. Q1 2022. There we go. Sometime in Q1. We're getting there. Ryan's really good too. He's another guy that will blow you away with his enthusiasm for this topic. It won't tie to a cert immediately. SANS goes through a process of trying to figure out it's hard to decide what to do. So it's kind of like a chicken and the egg problem. They look, see if a course has a lot of demand, then they'll add a cert to it. And then problem is that a lot of people, for some reason, I don't know why, they think if it doesn't have a cert, they won't take the course, which doesn't make sense to me. And so they don't get as much demand for courses that don't have a cert. So it's a weird process. The instructors are not in the loop on that process at all. It's purely SANS and GIAC, and they talk to each other and decide what they're going to do. I suspect there will be quite a bit of demand for a ransomware course because it's pretty hot right now. Yeah, yeah. So Nick, I kind of agree with you there because the cert for me, it's not so much that I have the cert, it's that it forces me to study the material deep enough to pass the test. And so I will go back and after the week, I know that I'm not going to learn the material in 1 week. So it forces me to go back and learn it over a period of another 4 to 6 weeks of study, prepare for the cert, and then I take the test. And then for me, I always have a goal of 90 or more. If you get a score of 90 plus, you get invited to be on the SANS advisory board. You'll be on the mailing list, and then you can hang out with us cool kids, I guess. But to me, it's making sure that I know the material, and doing the exercises is the #1 way of doing that. And then I have my index so that I go back and I can look at I can look up anything that might be more knowledge based. Maybe I missed a little detail, but I really do focus on the exercises and the hands-on stuff. All right, it is 5 o'clock. We are done with day 5, and tomorrow will be CTF. I'm going to stop sharing my screen. So Anne, thank you so much for the work you have done this week. Really appreciate it.
Thank you so much for the training. I really enjoyed it.
And everybody, remember to get the materials copy paste out of the Slack sometime. It'll be up for at least for a few hours after the class tomorrow, but I would do it as soon as you can after class. I would collect all of those resources that you're interested in. All right, talk to you guys tomorrow.
Take care. See you tomorrow. Have a good evening.